All right, so in this lesson here, in this lecture here, let's particularly look at how we can apply our skills, our understandings about logarithms into solving equations that's using logarithms. Okay, and so in the way how I see it, this is a way how we can, this is some further applications of how we can use logarithms, okay, outside of learning about the introductions and the properties of logs. And so in that way of how I'm saying, it is strictly required that this lecture here must be viewed or must be learned after you have already learned from my introduction to logarithms. Learn from that video lecture of mine about how I introduce what logarithm is. And then this is also required that you view anyone learning this lecture after you have already learned about all of the properties of logarithms. So you are required to be fluent at least at some point, being familiar enough with all the properties of logarithms. Okay, and further know how to work with logarithm functions and understand the graphs of a log of any logarithm function. Understand that a logarithm can become a logarithm function. Okay, so other than that, now let's get to work here. Okay, and let's see the ideas how we can apply our understandings of logarithms into solving equations that using logarithms. Okay. All right, so we have seen some of this basic idea previously already and when I said previously, I meant we have seen that some of these are basic problems back in the lecture where I was introducing about logarithms. Okay, but now we're gonna look into the even more advanced kind of problems. Okay, and so now before I really get into this, any one of these applications right here, allow me to introduce some further. Now these are also properties. Okay, some further details to understand, to take, but they're just consequences of the properties we have learned earlier. Okay, all right. So now this is one important understanding to pick up right here before I get into the next thing. So if we have two expressions that are equal, let's start out with any two expressions that are equal. So A and B, these are two quantities, two expressions that are equal. So we have an equality between two expressions, A and B. So that's given. So let's start out with that. So if that's so, if that's true, then now this is a proven fact as well. This is a proven fact right here. But so taking a logarithm, regardless of what base, whatever base, you can see that I accidentally wrote natural log. It's just my habit that I work with natural log for a lot more often than other logs. But generally speaking, once we're starting out, once we have any two quantities here being in an equality, okay, any two quantities here being equated together like this, then we can equally take logarithm in respect to any base. And of course, again, let's assume that at this point that any base we're using in a logarithm already met all of the requirements to be a base, okay, of a logarithm. And so now if A equal B, if these two expressions, these two quantities are equal, then taking the logarithm of the expression on the left hand side, okay, and in respect to base A, so take log base A of the capital A expression will also equal taking the logarithm of same base of the expression on the right hand side. Okay, and so what I do in the way how I see here, and the point now is that anytime we have two equal quantities or two equal expressions like this, then taking the logarithms, okay, taking logarithms of whatever base it is, but taking logarithms of the two expressions here will still maintain equality. Okay, so equality is still true after we take the logarithm on each one of these quantity A and B like this, provided A and B are equal. All right. So with this property right here, of course, I mean, let's get to the practicality of that. There is a proof for this, but so when I was saying, of course, earlier, I meant, of course, this was proven, but for the practicality of our course that we're learning, we don't need to dive too far into how past mathematicians have proven this, okay? But let's just directly get into using it, okay? See how useful it can be in terms of doing our work. All right, and so now I'm going to leave this here for a little while. All right, let's get to work with our first example right here. Okay. All right, so now allow me to introduce example 1. And so now, just as the title of our discussion topic here was stating clear, here we specifically solve equation where we are using logarithm we're bringing logarithm, our understanding of logarithms into solving an equation. And so now any one of these examples I'm about to bring in right here, we're going to get straightforward into using the term solve the equation for an unknown, solve the equation for an unknown, okay? So now I'm going to say solve the equation, okay, for the variable x. So the unknown in our equation here is going to be x, okay? All right, so now let's look at our first equation. So part A of this example. So now we have 4 times e to the 0.02x and equals 5. All right. So I've had a few equations that I've prepared in my lecture notes here and ready for showing through the video lecture here. So the equation we have here is 4 times e to the 0.02x right here, and we want that equals 5. Okay, so in the way how I see this is an equation. We have 2 quantities, left and right. These 2 quantities, we want them to equal. So we want to find out what's the value of x, what value of x satisfying left hand side equal right hand side. Okay. And so now the whole idea of solving equation now is that if we know if these, so we're going to start out by saying if the logic here is if these are equal, if these 2 on the left and the right were equal. If that was so, then we can apply that understanding we've had on the left hand that I had on the other board right there. See, so now because the logic for solving any equation, we always going to start out by, hey, if they really are equal, then what's going to happen? Eventually we break things down, and this is not new at this point. This is anyone who has already learned how to solve some other kinds of equations before. That's the way how it works. If the equation really is true, then consequently what leads to the next thing? Okay, and then eventually we're going to trace down from that. We keep leading down to our clues and leads down to a final value that must come out for x, for the unknown. And so now in this work right here, we've learned a further fact that if we know that 2 expressions are equal, then now we can take this logarithm, one same logarithm on both expression a and b right there, and we can still maintain equality. Okay, and so now, so in this equation right here, here's how I apply that understanding that we just now picked up right there. All right, so if that's true, if this is what we want, then okay, so I'm going to use an arrow indicating that the next step, if this is what we want, then taking log, now we can choose. Now that understanding I brought in earlier, that property I brought in earlier, that theorem I brought in earlier on the other board, there was no restriction about what base to use. There's no restriction about what base to use. Okay, and so here we have common log being log base 10. We have natural log being log base e. Okay, and so, and like I said, using a logarithm of any base is completely on our choice. The theorem that was stated on the other board does not have any restriction about which base we have to use. It's just generally as we apply a logarithm. So any base work as long as the base meets the requirement to be a base. Okay, and so here for to make it direct for us, okay, we can use either log base 10 or log base e, the natural log, okay, but only choose one of the two. We don't need to do both, okay, because do both means we just repeat the work. But once we go with one choice right there, we stick with that choice, okay. And so here I go with how about I just now change my mind a little bit. I go with the natural log here. All right, so now I'll go with natural log. And so back to the logic, the flow of the logic here. I was stating that if this equation is what we want, if we want 4 times e to the 0.02x to equal 5, if that's true, the case right there, then we can take natural log, the log base e of the expression on the left, 4 times e to the 0.02x, okay, and equal natural log of 5. And this is exactly how I apply that understanding, that theorem I stated on the other board right there. If we have an equality of two expressions, then applying logarithm of any base, okay, but once we chose a base, we stay with that base. Applying a logarithm to each side right here, okay, we'll still maintain the equality, okay. So now the logic here is if we know this is what we want, then we lead to taking logarithm on both sides. It's now another way that we can officially say taking a logarithm on both sides of an equation will still maintain equality, okay. So now why is this theorem useful for solving equation? Because here, once we apply that work taking logarithm, here I use natural log as a choice, but taking logarithm generally on both sides of the equation, okay. So here's the good usefulness. You see, if we look a little closer at our beginning equation here, one side of that has one side here, make a good note of that, this is exponential. One side come out as from an exponential function. All right. One side of our equation has an exponential function involved. As long as we recognize an exponential function involved in our equation, then using that, so now all of a sudden we realize it becomes a technique, it becomes a method that anytime we're solving an equation where we have an exponential term involved, okay, then simply take the logarithm of both sides. But so I keep beating around the bush, but what's useful about taking a logarithm on both sides of an equation where exponential function involved? Okay, what's useful about that? So let's head on to the next step right here to see. So at this point, this is where I was saying earlier that we're applying our understandings from all the logarithm properties and all of we apply all of our understandings about logarithm into this. Okay, it's a good place where we apply our logarithms, the understandings right here. So it's a product. On the left hand side, it's a product of 4 times e to the 0.02x right there. Okay, and then the right hand side is quite at a dead end already. It's just simply a constant value 5, and then taking the logarithm natural log of log base e of 5, it's just simply going to be a value. On the right hand side, it's just now a matter of pulling out a calculator and get a value for us. So we can still hold on to that. Okay, so the right hand side won't need much to be done there, won't have much to be done. But the left hand side, as I was in the, about halfway of saying it, we had a product, and then inside of this product we have in this product right here, this term here is exponential, it has a power. All right, and so we have gone through that lesson where we study closely the properties of logs. And then I've also had examples there where we've learned how we can break this expression down. We can rewrite this expression as multiple terms involving logs. So this is what I'm doing. So assuming that you have already learned from my earlier video lectures about the properties of logarithms, then here just allow me to apply those properties. So in my lecture there, I call there was property number 4, property number 5, allow me to be consistent with that lecture, like that. So property number 4 allows me to, first of all, break this product. And also in that lecture, it is extremely important that you got to view that lecture where I introduced the properties of logarithms before we arrive here. Okay, so once again, if you have no clue about what I'm talking about, I have a lecture where I introduced, I titled that, I call it, it's the properties of logarithms. View that lecture, get familiar with all of the properties I've introduced there, and then we resume the video here. So now in this video, allow me to assume that you already know what I'm talking about and familiar with these properties I brought in the earlier video lecture. Okay, so now, because I explained also in that lecture, I explained why I'm doing a step before some other step, why I'm taking some operation before some other operation. So now with this product, I'm going to break it down as a sum of two logs. So now it's a natural log of 4 plus a natural log of e to the point 02x. So just from logarithm natural log of a product here, it's the whole thing is a 4 times e to the point 02x. But now I break that product. I see logarithm of a product. I break it down as two separate logs, same base. Okay, but it's a sum of two separate logs. And again, all of this details, all of these understandings are explained in detail in that lecture I posted earlier, I brought in earlier, where I introduced all the properties of logarithms. All right, and so now this natural log of 4 is already another constant that we have just produced, because 4 itself is a value, is a constant value, and then taking the log base e of 4 is simply going to give us just another value. So that's good there, nothing much needs to be done there. But now this logarithm right here is where we can apply some further, where we can have some further work applied to this right here. It's a logarithm, but now inside of the log we have a value being raised to a power. Another property of log that we've learned from that lecture there can be applied here. All right, so in my next step, the natural log of 4 can be kept the same here. Okay, but the right hand side here now with that property number 6 that I introduced. So again, allow me to be consistent with the order of those properties, but you know, for other professors, they may name that, they may number those properties differently. But I'm assuming that anyone viewing this lesson here is already already viewing this after you have already viewed that my earlier lecture where I introduced all the properties of log. So I call that, it's a property of number 6, where we can bring an exponent down to the front as a coefficient. So how we apply that here, this is how we apply that here. I'm going to add, okay, due to that plus sign, 0.02x, okay, times a natural log of e. That's the property number 6 I was talking about right there. The power now just simply become a quantity or an expression multiplied in front of the log. And then the value inside, the expression inside becomes just simply that base right there. That value e with power 1. All right, so now I'm done breaking out down the left-hand side. The right-hand side here remains the same natural log of 5 the whole time. All right, so at this point right here, at this point, let me highlight a few things for anyone to realize. So in the end, really, it seems complicated, but actually it's not that bad. This is, I have to address that. This is constants. It's a constant term. Okay, const is short for constant term. This is also a constant term. Okay, and then in this term right here, we see the variable. So we want to solve the equation for the variable x. So this is pretty much the only term. And the reason I said these are the constant terms because they are completely independent with x. They have no x involved in any of one of these two terms like that. The unknown variable is not associated with any of one of these two. Okay, so those are constants. Now the only term having the unknown is here. But the way how it is, it looks a little complicated at first as well. At first sight, it looks a little scary. But this is just a coefficient. And by the way, natural log, see, log base e of e. We've learned from that property, log base e of e equals 1. So really, all of that middle term here becomes all of a sudden it shrinks down. That middle term that has it looks troublesome at first, but altogether we realize, hey, this natural log of e equals 1. Okay, equals 1, and then all we have now is just 0.02 times x. okay, times 1, and it's ridiculously needless that we write the 1 right here. So I'm gonna just erase that. So the whole lengthy expression here becomes simply just 0.02x. And now the natural log of 4, the constant term that I indicated, and that these are now like terms on the two opposites, on the two sides of our equation. And so now we come down to that usual step. We want to leave all the variable terms on one side and the constant terms to the opposite side. So that means, now allow me to erase this. Okay, and for anyone viewing the lesson up to this point, you allow me to assume that you are advanced enough now in your math learning. So the next step I'm doing here, I'm going to subtract natural log of 4 from both sides, leaving my equation, because I'm running short of space here, so leaving my equation 0.02x to equal the right hand side here becomes a natural log of 5 minus natural log of 4. Natural log of 5 minus natural log of 4. Okay, 0.02x or 0.02 times x equals natural log of 5 minus natural log of 4. So we are really that close to solving this equation. Okay, so now I'm going to navigate to the other board and continue the next step like that. All right, so now from the most recent step right here, I'm looking at 0.02x equals natural log of 5 minus natural log of 4, and this is all constants. So in that case now, I am going to just simply divide both sides by 0.02, the usual work of solving an equation. So that leaves me in my next equation, x equal, so now natural log of 5 minus natural log of 4 divided by 0.02. So this is our value for x that solves the equation. It's the value for x. Okay, so this is in exact expression, but if anyone desire to look for an actual, so this is the value. Okay, we're done, but it's written in exact expression. So if anyone, back to what I was saying earlier, if anyone desires to see the actual decimal value of this, okay, let's find out. So now we need a calculator to get through this. Okay, so before the calculator, and this is also, again, this is where a perfect place throughout this entire lecture, I can keep bringing in the properties we have learned from the earlier lessons, like from the most emphasized one is the one where I introduced the properties of logarithms. Okay, properties of logarithms, so important. Okay, it's a difference, same base on the logs right here, difference of two log terms. So now before I use a calculator, we do need a calculator for this, but before I use a calculator, we can speed up the process a little bit. This is still, I'm still beating around the bush a little bit. This natural log of 5 minus natural log of 4 is the same as a natural log of a 5 over 4 fraction. All right, and then we're going to divide. So once we have obtained a value from the calculator for this natural log of 5/4 right here, we can divide that 4.02, and that will give us our answer. Okay, so now the calculator will become very handy right here. All right, so now on the calculator, it's now just a matter of accessing that LN key, and then I'm going to type in 5/4, and then close up parentheses, and I'm going to divide by 0.02. All right, and thankfully our advanced calculators in these days, the standard TI 83 or 84 is strong enough, okay, to do this this entire computation in one syntax, in one command right here. All right, now let's hit enter, and so the value comes out here is approximately 11.157, and then rounding to for my lecture here, I decided to round to 3 decimals. All right. So for this equation, we have found the x value that's satisfied this equation is approximately about 11.157. All right, it's approximate. Okay, and so let's talk about this problem in part A a little bit more before we're completely done with that. Okay, so the essential theme here, the essential method introduced in this problem was, allow me to again write this in a small space right here, but it's all about if we know that we have two expressions equal to each other, then we can always take logarithm. Okay, whatever base that we choose, but once we have chosen a base right there, we stay with that same base for the two expressions. So take log base A of the capital A, and take log base A of the capital B expression. The two new expressions here will still maintain equality between them, will still be equal. Okay, and then we use that understanding here, we use that, now we apply that as a technique, as a method to handle equations that involve exponential terms again. Okay, and so in our problem right from the start, I made that note that before I even apply the technique here, I made that note that this equation, okay, and the whole reason for using logarithm is that this equation has the terms or even some other equation we're about to get in, we have even more terms around the equation left and right there, but it has an exponential term involved. All right, and so the usefulness of applying a logarithm on both sides, and I chose natural log. Anyone trying the problem here, you can also repeat all of these steps using the log base 10 as well. Okay, any log will work. Okay, any log will work. And here, well, here I noticed the problem itself has a base e, so we already had a direct logarithm that works with this e and makes things perfect right here. Natural log of e is a 1. Okay, and that's why I made that choice. Okay, and believe me, as you learn through this, and the more you work after outside of learning from the lecture right here, the more you work through the problem, the more experience you will build on your the skills here. All right, so the major method being used here is that anytime we're solving an equation that there's an exponential term right there, and we're gonna take the logarithm of both sides. Okay, take a chosen logarithm of both sides, apply a logarithm on both sides, and then from there, one side it may becomes a constant term, the other side, the whole point now is that it's going to break down, and most importantly, it brings that power down. See, it brings the 0.02x, the exponents here, down as a quantity to multiply with the logarithm, and then from there we can solve for that. All right, so that's a method right here. And then another thing I would like to point out before I'm completely done with this problem. So what I emphasize here in example 1 and in this lecture is a technique, is a method to solve an equation that involves an exponential term like this. Okay, but then for this easy equation, I still see that easy equation. Believe me, you have already seen something very similar to this in our lecture where I introduced about logarithms. Okay, we don't have to. I mean, sometimes for easy equation like this, you also have another choice of methods, a different method, an alternative method to handle the problem. So recall from our lecture where I introduced about the logarithm. Then with an equation like this, we don't need to think about sometimes I shouldn't say we don't need. Okay. As a matter of fact, applying the logarithm, I would like to push that as a more general methods. But for an equation like this, sometimes we can just stick with the solution, the method that we've used in that lecture where I introduced about logarithms. You see from beginning, 4 times e to the 0.02 x equals 5. I had in that lecture there, the lecture where I introduced logarithms, I had those examples where I call find the x value satisfying left hand side equal to right hand side. Okay, but in that, so that way of wording there in that lecture is exactly the same logical meaning as solve the equation for x. Okay, But now the solution there, the method I used there was simply just to extract out. So divide both sides by 4, and we got e to the 0.02 x equals 5/4. And then when we ended up with that one single term of exponential and equal a constant, okay, then we just immediately, we saw this in my, according to my explanation there in that lecture, we saw this as an exponential form of an equation. And then we immediately turned that into the corresponding logarithmic form. So it's base e here, so we turn that into log base e, or notation, as a notation, log base e of 5/4, okay, to equal 0.02. And so this magic point right here, truly is the same as this step. Because think about this step right here. This step where I have 0.02x equals natural log of 5 minus natural log of 4. This natural log of 5 minus natural log of 4, with our understanding about the properties of log, it is the same as natural log of 5/4. And so when solving for that, I was dividing both sides by 2. Okay, and so with an equation like this, so my point now, again, with an equation like this, applying that general method, applying logarithm on both sides may be a little longer than the method we used to know. But the reason I bring it in because I just want to start generalizing a one common method, because this way how we solved it back in that earlier lecture was good. It was good, short, nice, but it's limited to only those equations where it's one single term of exponential and equal a constant. But now later on throughout this example 1 in this lecture, we are going to be exposed to even more complicated equations. So we stick with that method we learned here in this lecture, apply or take the logarithm on both sides of our equation. Okay, that's the method that I would like to push into anyone learning from the lesson here into using that a lot more often. Okay, so I would like to generalize that method. All right, so now we are ready for part B of the example. And at this point, once you have already had some experience with after part A and where I put in a lot of details, now we can start picking up pace a little bit. Okay, we can speed up the process a little bit. Okay, so part B right here. So 3 times e to the 0.09x, and that equals e times 0.14x. All right. And this is where I'm saying, the technique, the method we already learned back in that lecture where I simply introduced about logarithm. That method there no longer works here, or it doesn't work too well here, because what we have here is now, it can still work, but it's going to take a lot longer. So the observation now is that we just have 2 exponential terms on both sides, right? And they are just, we have no constant terms involved. Good thing we have no constant terms involved, okay? No constant term, it's just coefficient with one of the exponential term, and then on the other side it's another exponential term. Having equal base here is not really important, okay? But now after pointing out some specialty of the equation here, all I see is I have 2 separate exponential terms on the 2 sides of our equation. Okay, so our equation now is completely exponential equation. Yes, you may hear some people here and there refer to an equation like this, an exponential equation, because it involves exponential terms in there. Okay, and so now as soon as we land into that form right here, 2 exponential terms equal each other, I'm going to directly apply. So right from this equation, the next step here is to apply it. So now we have seen that this from the earlier work already. I'm going to go with natural log of 3 times e to the 0.09x. See, I applied the logarithm that I chose. I apply that logarithm on the entire left-hand side. My entire left-hand side is 3 times e to the 0.09x. Okay, and that's why I put the whole left-hand side in parentheses, and then inside my logarithm. And so if I did that to my left-hand side, I'm going to do the same, taking the logarithm base e. It's a choice. On the right-hand side, it was e to the pointer 14x. All right. And so now by doing that, here's what I'm seeing next. Okay, so you have seen some action here from my previous part A right there. Okay, from my part A previously done, and then you have seen a lot of my explanations where I explained that we have to bring in a lot of properties from our lecture that we'll study the properties of log. And so now I see that again. There's a product, okay, 3 times e to the 0.09x right here. So now I'm going to immediately break this into 2 terms. Now one term is a natural log of 3. Now the other term is connected by the adding right here, connected by addition, plus natural log of e to the 0.09x. And we want that to equal natural log of e to the 0.14x. All right, that's how it works. And then now I'm not going to worry about moving the term yet. Okay, admittedly this is a constant term, similar to the one we've seen in part A right there. All right, so now in my next step, I'm going to still leave this constant term the same, but again, similar to part A that we've done, and this is all about we apply that property. Logarithm of an expression where power is involved, exponents is involved. Logarithm of an expression where there's an exponent involved. So that means I can apply that property we've learned previously about how we take logarithm of an exponent right here. So that means now for this term, I am going to bring this 0.09 in front. And then at the same step right here, I'm doing that. I'm bringing that 0.14x right here to the front. So now my left-hand side becomes 0.09x and multiply with natural log of e. The right-hand side becomes 0.14x. Multiply with natural log of e. Okay. And so now these natural log of e becomes 1. And again, this comes out because we've had that property log base a of a number a, log base e of e, log base a of a equals 1. That's just a reminder of those easy properties we've learned. Okay, so hopefully as we keep progressing through the lecture here, you will start building and be reminding your experience from that earlier lecture. Okay, and then the more we move on, the less I have to mention or remind about these properties that we've learned. So that becomes a 1. That's why I canceled it out. Really, it's a 1. So 1 multiplied with that. We don't need to write the 1. And that's another 1 right there. So I'm not really canceling it, just indicating it becomes 1. It becomes a 1 right there. All right, so in my next step, the equation becomes a natural log of 3 plus 0.09x. And that equals 0.14x. All right, so now we are ready to move terms around. Okay, all the terms with the variable, let's move them to one side. Let's bring them to one side, and the other side is just the non-variable terms, or namely the constant terms. So now in my next, so I'm running short of space here, so allow me to move on to the other board of mine right there. All right, so allow me now to just put this special fact that we understand here in a small space of this board right here. So anytime we have a equals b, then we can apply a logarithm to a on the left and apply that same logarithm to b on the right hand side and still maintain equality. So let's hold this here for at least a few more problems. And now I'm going to use the remaining space to continue solving our work. All right, so from the previous step, we arrived at the following. Natural log of 3 plus 0.09x equals 0.14x on the other side. So now we can just, as usual, this is the x term. My aim is to bring that to the other side. So I'm subtracting 0.09x. And that's just for me that I feel I need to do this to ensure anyone is understanding, but I doubt if anyone need me to explain about this. Okay, so natural log of 3 equals 0.14 minus 0.09. Okay, so that gives me positive 0.05 x. All right, and so now we are so ready. This is just a linear term. Yes, a little bit of an ugly looking coefficient here, but it's completely doable. Okay, we can completely handle this. So I'm going to divide both sides here by 0.5. I mean 0.05. So I'm now ready to calculate my value for x. See, x equals natural log of 3 divided by 0.05. This is an exact expression. Okay, and then now we're going to head over to our calculator to obtain a final approximate value in decimals. Okay, so x is approximately all right, so now with the calculator, right, so now I was doing natural log of 3 and divided that by 0.05, and I wrote 0.02. So it needs to be a 5 here. And now the answer is about, it's approximately 21.972 right there, 21.972. X is approximately 21.972. All right, and that's how we have solved another exponential equation. Okay, exponential equation. Simply, that's where we have exponential terms involved. All right, so I'm not saying we have reached to the most complicated yet, but at least we have reached to the final form of these, the final forms that we mostly run into throughout our learning. Okay, I'm not saying that these are all for exponential equations out there, but the one we're looking at right now is we have two exponential terms simply equal to each other, and then no constant term involved. And then this is the form where anytime you're working with an exponential equation, this is the form where you see the most. Okay, where you see the most. And then if we have a constant term added somewhere here and there, we need a different technique. So this technique we're learning here, applying a logarithm on both sides, is particularly good for where we just have, the one single term on the left and one single term, the exponential term on the right. We've got two separate exponential terms, but no constant term involved. Okay, and then this is where that method, taking logarithm, whatever base that is, taking a logarithm on both sides will handle all problems. Okay, but allow me to get into some more, to bring in some more advanced, even more advanced problem now. So advanced here just is simply in a sense that right now it's still simpler in the way that it's the same base, and it's a base e. It's a base e. So I chose a logarithm simply because it works directly with base e. Logarithm is log base e. Natural log is a log base e. Okay, so log base e of e, it makes things more direct. So consequently, when it came down to here, we have a quick calculation for that. We can have a quick mental math value for that. All right, let's get into another one. All right, so let's look at part C of our example, and let's solve for x again. Let's solve the equation for x. And now I want to look at about 4 raised to the power of 4x minus 7 equal 3 to the 9x minus 6. All right, so the equation itself admittedly looks cleaner than the earlier one, but it's indeed slightly more complicated than the earlier one I brought up in part A or part B right there. Okay, in a sense that in part B, we already had two exponential terms, but they were both of the same base. They were both of the same base. So we can choose a base that works directly. So that's why I chose natural log to work with base E in that part B, in that problem of part B right there. But here we got two different bases, completely different. I mean, there's a base 4 here and then there's a base 3. Okay, these are two exponential terms right here in our equation, left and right. Left is base 4, the right hand side is base 3. Okay, so there's no there's not really any longer a satisfying logarithm that works with both base here. So we just simply pick a base. We pick a base. We're just simply going to pick a base right here. And so now I'm going to stick with base e again. Even though, so at this point you can go with base 3, and you can go with base 4, you can go with base 5, whatever base right there. Okay, but I'm going to stick with base e, the natural log, because it's just me. I'm more familiar with natural log. But base 10, log base 10, the common logs work exactly the same way. Okay, we're going to have to spend the exact same amount of steps. And using a general log, like a log base 3 or log base 4, we'll also walk you through about the same amount of steps. But other than that, log base 5 will work, log base 6 will work, but it's going to produce more steps. Okay, and so now I just want to stay with the natural log, the log base e right here. So I'm going to apply. So if we want that 4 to the 4x minus 7 equal 3 to the 9x minus 6, then, okay, taking the natural log on the left hand side, that's why I put parentheses now, 4 to the 4x minus 7 will equal natural log of 3 to the 9x minus 6. That's the logic of an equation like that. Okay, and so now I apply logarithm on both sides of my current equation. If I want that equation to be true, if that equation is true, then taking the logarithm is also true. Okay, and then we keep leading down, and then eventually we're going to break down some value for x. All right, so now I'm seeing that property where we have learned before, and I've mentioned it a couple times already. Now, so now I can bring this exponent right here to the front as a quantity, as an expression that multiply with my log. So 4x minus 7 is brought down and multiply in front of natural log of 4. So natural log of 4 now is all of a sudden a coefficient to multiply with this entire the 4x minus 7 expression right there. All right, and now on the right hand side, it produces for me 9x minus 6 is brought down in front of the logarithm, and now I have a natural log of 3. All right, and so that method now really, I hope I have struck a clear good news into your mind right there. We have a clear-cut method. It may take some time, but it's a very solid and general method. Take the logarithm on both sides of our equation anytime we're solving an exponential equation right there. And then especially it's so useful where the two terms are just any two exponential, single exponential terms like that. Okay, so now let's continue. And so now let's treat the natural log of 4 here as a value, as a constant value. So I'm going to distribute that for each term here. I'm going to distribute the natural log of 3 on the right hand side here to each term. And so now my left hand side gives me 4x times the natural log of 4 minus 7 times natural log of 4. That's what I did, distributing the natural log of 4. That equals similarly 9x times natural log of 3 minus 6 times natural log of 3. All right, and now these are constant term, or in another way of saying these are like terms on the two opposite sides right here. And then these are like terms. We can rearrange the terms here. So now I'm going to bring the 9x here to the other side, and I'm going to bring all of the 7 natural log of 4 here to the right hand side. All right, so now I'm going to add 7 natural log of 4 to both sides. Okay, and in the same time I'm going to subtract 9x natural log of 3 from both sides. All right, so my resulting equation is going to become as following. We have 4x times natural log of 4 minus 9x times natural log of 3, and all that there equals 7 natural log of 4 minus 6 natural log of 3. All right, and that's how that's how I got to that. So now I just want to point out, or maybe let's move to the other board, and then I'm going to rewrite this step right here on the other board so that we can have a little bigger space right there, and we can view things a little better. Okay. All right, so from the most recent step right here that we were at 4x times natural log of 3, natural log of 4 minus 9x natural log of 3, and all that there was equal to 7 natural log of 4 minus 6 natural log of 3. Okay, admittedly the right hand side now is entirely constant. The left hand side looks admittedly a little confusing at first. Okay, but in the end it's just because these natural log terms, it's just we are not too familiar with seeing things like that, but it's a coefficient. Together with the 4 here, it's a coefficient. So x is the unknown. So it's really 4 times natural log of 4 times x. This is 9 times natural log of 3 times x. What I'm trying to point out now is that we can see the x here as a common factor. Okay, so now I'm going to factor out the x. Okay, and then we have left behind 4 natural log of 4 minus 9 natural log of 3. Okay, and equals 7 natural log of 4 minus 6 natural log of 3. This is an expression that will completely give us a value entirely. It's completely doable to get a value there. And this is another expression. This is another expression where it will definitely give us a known value. It's not like an unknown. The x here is the unknown. Okay, but now we can find out what value for x is. So x, now we can just simply divide both sides. I'm dividing both sides here of our equation by 4 times natural log of 4 minus 9 times natural log of 3. All right, and so the ending equation, the left-hand side cancel that large expression completely. Now it leaves out behind for me x equals 7 natural log of 4 minus 6 natural log of 3 and divided by 4 natural log of 4 minus 9 natural log of 3. And then, so this is an exact expression. This is an exact expression. But then here's the thing. If anyone desire an actual numerical value in decimals here, we don't rushly type this into the calculator. It will work. Just typing this into the calculator will work. Okay, but here's the thing. Once again, let's use as much as we can let's use our understandings of the logarithm as much as we can. Okay, so that it can assist the calculation process. It can be useful for the calculation process. Coefficient of a logarithm. So we can turn that into a natural log of 4 to the 7th power minus natural log of, so now in that way I see natural log of 3 to the 6th power. 3 to the 6th power. And then dividing that by, I'm doing the same work here, the same trick here. Natural log of 4 to the 4th power, okay, minus natural log of, this is 3 but to the 9th power. 3 to the 9th power. All right, and then, well, I'm running out of space here, so allow me to just erase that. Now, have that observation carefully right here. And 4 to the 7 is admittedly a little big right there, so I don't want to write down all the digits like that. But it's just simply a difference of two logarithms, same kind, same base right there. So that top right there, I can rewrite that as That top right there before, this is, I'm talking about, let's do some prepping work before typing it in the calculator. So it's a natural log of the 4 to the 7 over 3 to the 6th power. It's one expression right there, but now we have less operations to involve. Okay, and then the denominator here, I can also put that as 1 logarithm of 4 to the 4th minus, divided by 3 to the 9th. All right, so now we're typing this into the calculator. It's less logarithm involved for us right there. All right. So now on the calculator, just like how I lay it down, there's some prepping work on the board right there. So now all I need is just a logarithm, a natural log. All right, so inside the log, inside of this parentheses, I'm typing 4 to the 7. Okay, for this calculator, for this advanced software of the calculator, I have to exit out of the superscript mode. And now I'm going to divide by 3 to the 6. Okay, so all that here is in 1 logarithm in the numerator. And so now I'm going to divide. Okay, so now just one more logarithm, the natural log in the denominator. And now we're looking at 4 to the 4th. Okay, exit out of the superscript mode, divided by, so all of this here is inside of my denominator logarithm. And now I'm dividing that by 3, but to the 9th power. All right, so now I'm ready to close parentheses. And so now this reflects exactly what I'm seeing on the screen right here. Okay, before I'm punching out down the button to get the final calculated approximate. And then, by the way, once I've had that calculated approximate, then I'm going to erase this expression right here and just simply write down that final approximate right there. Okay. So now back on the calculator, now we're ready to hit enter. All right, so the answer now is a negative 0.71675 and a lot longer. So allow me to round to 3 decimals, negative 0.717. Okay. So now we came to an approximate for x. All right. So x is approximately negative 0.717. That's about the value right there. Okay, so we can leave that in exact expression like this, or we can leave that in decimals like that. All right, so that's how it works. And once again, 3 problems so far in example 1, and I've brought you in enough situations like that. And we have seen that just simply get right into anytime we have an equation. And now for our kind of equation where exponential terms are involved, and we just get straight into applying, or taking a logarithm of whatever, of a chosen base, taking the same logarithm on both sides of our equation, and then our equation is then we're going to start applying our understandings of the logarithm properties to keep taking us to the next step and the next step. Every step after taking the logarithm on both sides will become slightly different here and there, but it's all about we apply our properties of logarithms. Okay, and then essentially again that this method is particularly solid for those equations where it's one exponential term on the left hand side and only one exponential term on the right hand side, no constant term involved on either one of the two ends right here. Okay, so the method we have here is designated for this kind of exponential equation. All right, and then if we step outside of these problems I brought up in example 1, then we need some other technique like that, and not necessarily using logarithms. Okay, so using logarithm here is good for this kind of equation, exponential equations where one exponential term equal one other exponential term, but that's about the most. No constant terms involved at all. Okay, so before I leave this example, let's do one more problem. Let's do one more problem like that, and I'll lead the way again. All right, so now part D of our example, and this is the last one in example 1 right here, where I introduced how we use logarithms, a logarithm into solving a lot of different situations in an exponential equation. Okay, so part D of our example. So I have now about 17. Okay, so 17 times 1.14 to the x equals 19 times 1.16 to the x. Okay, so with this equation here, now once again it's starting to look kind of all over, but in the end the whole thing here on the left hand side is one exponential term, and then we have another single exponential term. Maybe we have some coefficient, but these are coefficients, they come as a product with our exponential terms there. But in the end, the good news is we still don't have any constant term involved. And so as I said, anytime if our exponential equation has some constant terms involved right there, then we do need a different kind of technique right there, a different kind of methods. Not necessarily using logarithm, but here to use logarithm and directly apply logarithm on both sides right here. We're handling perfectly with these equations where it's one exponential term on one side equal a one exponential term on the other side. We do want to bring that into that form like that. So before I get into this problem, so now generally this method we work with, this method we use work particularly good for some a times a to the x times b to the x. Yeah. This is what that equation generally is. But no constant terms involved. So anytime we're having an equation like this, okay, so any equation of that form, okay, can be solved by, okay, we take the logarithm. So I use generally here I use a natural log, but you can use whatever log that you want, whatever base of the logs that you want, as long as the base is convenient for you, that you're comfortable with. So now I use natural log here, but apply the same log on both sides of our equation. That's the method. All right, so now I wrote it down, but sadly I can't leave it here for too long. I'm going to quickly erase that to once again bring this generality into solving our work with that. All right, so now right from this equation, I am going to take the logarithm and see the bases here are nasty. It's 1.14, it's 1.16. It's not even a whole value base. Okay, so it does not really matter anymore of what bases we use. I'll just get straight into natural log basis, the one that I'm comfortable with. You're more than welcome to explore your own your own logarithm that you're comfortable with. Okay, so here I'm using natural log. Natural log of 17 in product with 1.14 to the x. And so if I apply the natural log that I'm comfortable with on the left hand side, I'm going to apply the natural log, the same log. That's the point right there. Okay, 19 times 1.16 to the x on the right hand side. That's what we do. First big stepping stone for the entire method, and then from this step it's going to start taking us to slightly different directions here and there. But the point now is that it's all about bringing down. We have to bring down that power. We bring down the exponents. Okay, somehow. All right. So now it's a product here. It's a product here on the right hand side, and it's a product there that I have to put a big dot right there for anyone to realize. So the next step is to break down that product into a sum. So now I have a natural log of 17 plus natural log of 1.14 to the x. Okay, and then to the x, and then on the right hand side I have natural log of 19 plus natural log of 1.16 to the x. All right, so that's what I'm doing. And so now, in the next step, see, this is constant term, like term with this, natural log of 19. These are the log terms on the left and on the right hand side. Okay, so in my next step, I'm going to apply the property of logarithm again, another property of logarithm. And now at this point, I'm going to completely ignore about is that property 6 or property 5. It's you who viewing this lesson has to know that at this point. I mean, if you learn the properties of logarithms specifically for me, then I have my own way of numbering those rules like that. But if you learn that with anybody else, then make sure you have your little pockets reference handout that lists down all of those the log properties there with you. Okay, so now I'm going to apply that property where I can bring down the power, I mean that exponent x down in front. This x will come down in front. So for now, natural log 17 on the left hand side stays the same, but this term becomes x times the natural log of 1.14. So all certain things looks pretty good so far. All certain things turns out pretty good. Okay, and then equal natural log of 19 for now is kept the same. I haven't done any work on that yet, but we're gonna add now x, multiply it down, so x times natural log of 1.16. All right, so now the x times natural log of 16 is like term with that x times natural log of 14 right here on the left hand side. So in my next step, I'm going to bring that term, I'm going to rearrange this term to be on the other side. Now that natural log of 17 is like term with this natural log of 19. So I'm going to bring that natural log of 17, I'm going to rearrange that term to this side. All right, so that means I'm going to subtract natural log of 17 on both sides. See, subtract natural log of 17 on both sides. I'm going to subtract x times natural log of 1.16 on both sides. All right, so now I'm going to end up with my resulting equation as following. So the natural log of 17 cancels on the left hand side. The right hand side becomes x times the natural log of 1.14 minus x times the natural log of 1.16, and all of that there equals, so all of these are cancelled. So natural log of 19 minus natural log of 17. All right. And so now let's write down this step in the next space of my board right there. All right, so now from the very recent step right there, I'm looking at the x times natural log of 1.14 minus x times natural log of 1.16, and all of that there equals natural log of 19 minus natural log of 17. Okay, and so now on the left hand side, this is where all of the variable terms are here. Okay, so now all of a sudden I realize really just the natural log of 14 here is just a coefficient, even though we write that in the behind our variable. Okay, it's a little unusual with what we normally deal with. It's a little out of ordinary, but because it's such a big expression, so we, even though it being a coefficient, we write it to the back of our value right there. Okay, so x times this constant coefficient minus x times that constant coefficient again. So all of a sudden we realize this is just simply a common factor again. So I'm going to factor out the x, okay, in my next step, and produce, and now I'm going to produce let's use brackets here. Natural log of 1.14 minus natural log of 1.16, okay, equals natural log of 19 minus natural log of 17. Okay, a very clear-cut method there. Apply logarithm on both sides from one of the earlier steps. Now it led us to all of these here. All right, so now this is really just one coefficient, one big expression representing a coefficient. I'm going to divide both sides just by that. okay, by natural log of 1.14 minus natural log of 1.16, okay. All right, and so now I'm quite done with my problem. The left-hand side completely cancel that common factor. So now I have x equals, all right, and so now natural log of 19 minus natural log of 17, and I'm dividing that by natural log of 1.14 minus natural log of 1.16. So as far as exact expression, we're done. This, whatever comes out from this big, ugly looking expression, okay, but getting there is not so hard to me anymore. Okay, it was quite a clear-cut method. Okay, so x equals all that, and then for anyone who desires, and this is in case your own professor aside from me, is looking for a numerical value in decimals, then you can. Let's learn how we can type this in your calculator. Okay, and so now again, before you see, it would be very naive that you type the whole thing in here. Natural log of 19, maybe in parentheses, natural log of 19 minus natural log of 17, close parentheses, slash sign for division, and then parentheses and all that mess here. It works. It will work. Okay, but it takes a lot of time. It will take a lot of time. So let's do some prepping. Logarithm minus the same logarithm of, so that turns into a logarithm of a quotient. Numerator here becomes 1 natural log of 19 over 17. This is going to be a lot faster on the calculator. Okay, the bottom one, similar action can be done here. Same log, two terms connected as a difference. Okay, two terms in a difference. So a difference of two logarithms can be turned into a logarithm of a quotient. So 1.14 divided by 1.17. All right. This is what we can use for our calculation in the calculator. It's going to be a lot faster. Okay, less brutal for the calculator. Now, when classes are face-to-face, a lot of times when we're doing such a large computation like this in the calculator with a calculator, I feel that we are forcing the calculator to overwork itself, okay, to work over its capacity. So I keep making this joke. I constantly make this joke with my student that we brutally force the calculator to do its work, okay. But if that's the case, let's handle it. So now at least we have less calculation here. Natural log of 19 divided by 17. Okay, so this is the one numerator. I'm dividing that by natural log of 1.14 divided by 1.16. All right. And now the answer comes out minus 6.395, and allow me to keep, in this lecture over here, allow me to keep these values in 3 decimal places. So minus 6.395. All right. So now I'm going to quickly erase this. And as an approximate, our x value is minus 6.395. All right, all right, and a lot longer, but we only round to 3 decimals. All right, so that's all for example 1, and the essential theme again is anytime we have, and so now with so much things involved here, let me erase the work we have just done so that we can have a focused view on what I'm still leaving on the board here. All right, so this is what we've learned as a fact here. Anytime we have an equality, we can take the logarithm on both sides of our equality, and that still hold, the equality still hold true like that. Okay, and so particularly we use this known fact now as a method to solve. So anytime our equation, I brought this up earlier, anytime, okay, so for any equation, of the form a coefficient times a base to the x equal another coefficient times a base, a different base to the x, like that. Okay, then we can solve. Okay, we can be solved, right, by applying a logarithm. So I use natural log here, but it can be just log base 3, log base 5, as long as it's one same log for two sides. A times a to the x to equals same log b times b to the x. That's the method that came straight out from this, and along there we apply all the properties of logarithms that we've done. All right. Alright, so just now I've talked about how we apply logarithms into solving an exponential equation. But why do we even have an exponential? Why do we have to face with an exponential equation to solve? So first, at this point right here, maybe a major curiosity question popped out from your mind after you've learned through the whole example. So the whole example 1 was about introducing how we can solve it. But then now, why do we have to face these kind of equations? So that it create all of that kind of works for us earlier in example 1. Okay, so we've done about 4 problems. Let me pick about 2 problems to illustrate the idea right there. Okay, so we have already learned. So prior to this point, prior to learning about logarithm, anyone must have learned about an exponential function. Okay, and so let's say in part B of example 1, for example, okay? So back in example 1, part B, the equation we had there was 3 times e to the 0.09x, okay, equal e to the 0.14x. So I'm giving that explanation. I'm about to give that explanation of why do we even have this equation to solve for x? In what places will we have an equation like this? So that it pushes us into developing a method that we have used throughout example 1. Okay, what's the application? All right, so now an equality, needless to say, an equality equates to expression. So if we're now looking at the left-hand side and the right-hand side a little more closely, if we just isolate out the left-hand side, completely ignore the right-hand side and only focus on the left-hand side, the left-hand side is one exponential function. We can see this as one exponential function, f of x. So we have an f of x equals 3 times e to the 0.09x. That's the left-hand side. And so we've learned from our previous learning that this is an exponential function. The right-hand side, now if we completely ignore the left-hand side and only focus to the right-hand side, and if needed, just go ahead and define a function g of x to be e to the 0.14x. This is another exponential function. Okay, and so quickly on the graph. All right, so now on my empty graphing space, allow me to hide away all the grids and number labels, numerical labels on the axes right here. Okay, so now think about that f of x function. All right, so just now this is the graph for f of x equals 3 times e to the 0.09x. Okay, this is the graph for that function. And now this graph in blue right here is the graph for the other function g of x being e to the 0.14x. All right, so in this closed zoom level right here, then we don't see any intersection, but the point now is that solving this equation that same exact understanding we've been having since earlier course throughout our earlier part of the learning in this learning term right here. Anytime we're solving an equation for x, that means we want to find the x values satisfying our one function equal the other function, or where the two graphs in red and in blue here crossing each other. Okay, we don't see that crossing point yet, but now let me put it out in a further zoom level right here. Okay, all right, so now we start noticing they have some crossing point right there. Okay, and so now let me put that in full screen view. So in full screen view right here. Okay, all right, so if we look back at our work in example 1, this was the value that we found in 3 decimal places for. It was 21.972 right here. That was the x value satisfying the two functions, the two graphs. The graph in red is the graph for the f of x, 3 times e to the 0.09x, and the graph in blue is the graph for g of x, e to the 0.14x. But solving that equation means we want to look for the value where the two graphs are crossing each other. Okay, or an x value satisfying function f equal function g. All right, so that's the whole idea right there. So as another quick demonstration, okay, so in my example 1, but part D, okay, for example 1 part D, example 1D right here, the equation we've solved was 17 times 1.14 to the x and equals 19 times 1.16 to the x. Okay, so once again, we can just simply think about solving this equation means we want to find the x value satisfying f of x equals 17 times 1.14 to the x, and we can see that g of x on the right hand side can be regarded as another function, 19 times 1.16 to the x. These are all exponential functions. So we want to find the x values where the graph of this function crosses with the graph of the other function, or where the two graphs are crossing each other. Okay, or we want to find the x value satisfying f of x equal g of x vertically for the outputs. Okay, and so once again on my graph right here, this is the graph for f of x, 17 times 1.14 to the x. And again, I purposely hid away all of the grids and all of the numerical labels so that we don't have to worry about estimating. Okay, I just want to demonstrate that this is the graph for f of x, and now the graph in blue here is the graph for g of x. Now at this far zoom level, it's hard to tell. Okay, but now you can see that at some point the red curve is above the blue curve, and then at some other point the two curves twist over. So blue curve stays above the red curve like that. So there has to be a point where they cross. So now our work on the board earlier is to find out where can these where or which x value will the two graphs here cross each other. So now the value displayed on decimals here agrees with our work earlier on the board, minus 6.395. All right, so that's the value right there, and that agrees with the calculated value we have had on the calculator earlier. Okay, minus 6.395 in 3 decimal places. All right, and so the entire example 1 already demonstrated how we can apply the logarithm into solving exponential equations. Okay, so now let's explore a different way how we can apply the logarithm into a different kinds of equations. So we're still solving equation, but you can think about we're heading out of exponential functions. We can be done with exponential equations at this point right here, and let's move on to other kinds of equation right here where we need to understand the properties of log to get the problems solved. Okay, and so now it's a little hard to I mean, it's a little hard to generalize the idea here. So all I can say is just equation that involves log, okay? Equations that involve log. And so now I'm going to get immediately into the example, okay? I'm going to get immediately into the example, and then throughout each example will allow me to the first few few problems in the example 2 right here allow me to put in as much details, and then once you got in gear with the method right there, then we're gonna start picking up pace right there. But so the whole example 2 we're about to look at now is all about equation involving log, okay? Equations that involve log right there. But don't call them logarithmic equations actually, okay? Don't use that term logarithmic equations, okay? It's just equation that has log terms in it, but they are not necessarily logarithmic equations, okay? So now let's look at example 2. All right, so we want to once again solve the equation, the given equation. And I don't think I need to write that word given. So solve the equation for x. Okay, it's an equation, and as I mentioned ahead of time as a preview for anyone who's about to get into this example together with me, it's an equation. Any of the equation here has logarithm involved, right there. Okay, has the logarithm, the operation involved, right there. But we don't necessarily call these things the log equations. Okay, so let's look at the first equation right here. All right, so how about log base 2 of 7x plus 6 equals 3. All right, so welcome to this world where we're looking at an equation where we're about to solve an equation with log involved like that. Okay, so admittedly this particular equation in part A is the one that you can legally or officially call the logarithmic equation right here, and this is pretty much the only one. So what's in a logarithmic equation? A logarithmic equation is an equation where there's only one single log term. The whole thing here is one single log term. Okay, and it equals, and aside from that single log term, the opposite side is a constant. That's all it can be. That's all it can be. Okay, and so now before I get into solving this, see, I have to remind anyone in order for this lecture to be possible for anyone, in order to make it possible for anyone to learn through this lecture, you must understand what a logarithm is. So via my introduction, via my lecture where I introduced about logarithm, you must understand all the properties of logarithm, and you have seen how I emphasized that throughout example 1. And further, you must have already learned about how we can use a logarithm operation to create, to define a logarithm function, okay, a logarithm function. And so you have to know all of those details before arriving at this particular lesson right here, particular lecture right here. All right, so now the way how I see this now, one thing to be careful, among all the properties of logarithm, okay, among all the properties of logarithm, there has never been, so it's a warning right here. I keep having people as high as calculus courses of mine making the silly mistakes right here. I see students of mine breaking this logarithm because inside the logarithm, see, in earlier video lectures where I talked about the properties or the introduction to logarithms, I call this part right here the arguments of a logarithm. Okay, so log base 2 of that entire expression being the arguments. So the argument here has two terms. The expression inside the log here has two terms. Okay, I don't call this the input because I would like to see that the input is only the x right here if we give that different inputs, in case you already had learning about what a log function is. Okay, but back to the mistake that I generally see, and I want to point it out right here. There has never been a rule that that allows you to go breaking this logarithm into a log base 2 of 7x plus a log base 2 of 6, and then equals 3 on the other side. Please do not do this. This is very incorrect. Okay, recall. This is if we did it that way, I mean, here's my way of quickly explaining it. If that is equal to the sum of two separate logs, notice the way how we wrote it mistakenly, two logs, a sum of two logs, but of same kind right there. But we already had a rule. We already had a rule that's saying a sum of two logs of the same kind can be log base 2 of 7x times 6, meaning 42x altogether. 42x altogether. But so wait a minute. So if it's that way, if we think of it that way, this log equal to that, the sum of those two logs, and we already knew if we had the sum of the two logs, then it would equal to this. Then that means these two are equal? Not necessarily. Not necessarily. All right, so that's why don't break a sum inside a logarithm into two separate terms with logarithms. That's entirely incorrect right there. Okay, there has never been any rule guaranteeing that. I can see one reason why my students keep making that general mistake is that they, over time working with log long enough, I don't know why they and how they developed that understanding, but they mistaken the logarithm symbol here as a multiplication, and so they distribute the log with each one of the terms here, and that's how they consequently ended up with these. That's even another way off hook thing right there. Okay, don't get there. So now, what's the proper way of doing that? And then back to this equation. This is the only equation where I call it's a logarithmic equation, because one log term, and the inside here is a linear expression. I should have also clarified that. Okay, but we can also extend that to being a quadratic or something else more fancy, but one log term equals a constant. Okay, so now once we arrived at this point right here, then quickly on this board of mine, let me remind anyone the following important understanding that we should have already picked up before we enter this lecture over here. All right, a log base a of any expression x, that a log base a of any argument x that equals a value y means, we've had this way back from the lecture where I first introduced about logarithm. Okay, so a log base a of an argument x or a value x equal a number y means the same as a to the y equals x. See, logarithmic form, exponential form, logarithmic form, exponential form. Surprisingly, this understanding we picked up long ago now all of a sudden becomes a solid method of how we solve a lot of equations involving log. Okay, a lot of equations involving log. So how do I apply that here? You see, that's why I have to build your foundation from this simple one. One logarithm term, and it's not a product here. One logarithm term equal a number, and there's something inside of the logarithm. Okay, so now directly applying that, understanding that basic definition I've had on the other board, but I introduced that long ago for anyone learning with me. Then this equation means the same as the following: base 2 raised to the third power, okay, equal 7x plus 6. Okay, and once we successfully rewritten from logarithmic form to exponential form, and see, if you recall yourself once you've gone through my earlier lecture about how I introduced logarithms, then I've also had examples showing you how you can learn to rewrite an equation from logarithmic form to exponential form, and from exponential form back to a logarithmic form, vice versa. This is where that skill we've learned from earlier lecture applies here. Okay, So now, what's useful about doing that here? What's useful about writing this logarithmic equation into exponential equation, in exponential form here? You see now, 2 to the third power is clearly just a value. 2 to the third power. So we're looking at 8 equals 7x plus 6. Now take a moment to sit back and think through, how difficult is this equation? It's not that difficult at all. It's a very basic equation, basic linear equation that anyone can solve within seconds. Okay, subtract 6 from both sides. Yes, that's how we're doing it. Once we've successfully applied that step, turning from logarithmic form of the equation into exponential form of the equation. That's the key. All right, and then from there, it's going to start turning us into different equations being simple for us. All right, so now minus 6 from both sides, I'm looking at 2 equals 7x. Okay, and now I'm going to divide both sides by 7. Okay, and divide both sides by 7. So my allow me at this point, it's also one thing that doing any equation, solving any equation that has logs here, I have to move slowly and then bring in as much details as we can. Okay, the solution rate we're about to call that, allow me to call that just the tentative solution, the tentative x value, 2 over 7, meaning we found something, but I'm not going to say this is our answer. I'm not going to rushly say this is our final solution yet. We only found one value so far by going to the solving work. Assuming that you have done all the proper switch around and apply going from logarithmic form to exponential form and all that, etc., etc. Assuming you've done all that algebra correctly, and we have done to that point right there, we found a value for x. But let's not call that the final answer yet. Let's just call that the tentative answer right here. Why is that? It seems dangerous. Here's the reason why. So I want you, anyone viewing this lesson, anyone learning in this lesson, to nail down the following facts. Okay? Anytime you are solving an equation that involves log. Anytime you are solving an equation involves log. Okay? So I mentioned, and we've had examples in this about this in earlier lecture where I introduced about logarithm functions. Okay? And that's why, once again, it's extremely important that we only learn this lesson after we've already learned about my other lessons where I introduced what logarithm is, the properties of logarithms, and how we define a logarithm function. Because now if I see this left hand side here as a logarithm function, there's no need to see that as a logarithm function. But this whole thing here is a logarithm function. Okay? We need to be aware about the domain of any logarithm function. The domain of a logarithm function is important. Anytime we're working with a logarithm function, be clearly aware about the domain of a logarithm function. So now I'm not going to spend time showing how to find the domain of this logarithm function. That's for the other lessons where we've learned about logarithm functions. But here, the domain has to be any value of x greater than negative 6 over 7. Or in other words, in interval notation, the domain of this logarithm, log base 2 of 7x plus 6, has to be anywhere between negative 6 over 7 to positive infinity. That's the domain for this logarithm function. Okay? And so now, once we found, the reason I call this found value right here only a tentative answer so far, because it's just the way how we're solving these equations that involve logs here. There will be a lot of times where you found some solution, and sadly that solution of yours, assuming you did all the work correctly, but then unfortunately or sadly that solution, or maybe the only solution, fell outside of the domain. Okay, but that's not the case here. Gladly, we found a value, so I call that it's a tentative solution. And tentative now means let's check, is this answer inside the domain of our logarithm? Is this answer inside the domain of our logarithm. The domain is here. And yes, this answer is inside of the logarithm, the domain of this logarithm. So that's now not only a tentative answer, it is now our final answer. All right, so that's all that logic there. All right, that's what it is. So now, after this problem right here, in any of the later problems that I bring up, nail down the domain, okay? And I will, on my steps here, I will show the domain, but allow me to not go in steps how we got the domain, because that's came from previous understanding, okay? So I will just simply nail down and keep it a corner somewhere. But first thing in solving any of these log equations, get the domain of the logarithms, okay? And then from that point right there, we're gonna start doing our work. Okay, we're gonna start doing our work, and then we're gonna check. We're gonna check to see if sometimes we have one answers like this, one value like this. Sometimes we end up with multiples, and a few of them would fall out of the domain. Then we have to rule out those guys that fall out of the domain. Only take those that fall inside of the domain. And even in the worst case, all of the found values fall outside of the domain. No solution. Okay, that will happen as well. That can happen. I cannot guarantee any situation that happens in throughout our example here, but be aware of what I'm saying right there. Okay, so get the domain and then put it somewhere of your paper, of a corner of your paper, so that as you progress along the equation right there, and once you arrive at an answer right there, don't just rushly call that final answer, but rather call that a tentative answer, and then check with the domain. All right. So now let's move on. So after we have seen part A, that important step to be highlighted, aside from nailing down the domain, that important step is to use this experience. It's from our previous understanding that we are able to write an equation from logarithmic form into an exponential form. That's all there is. That builds the whole skills here that we're about to go through. All right, so now keep that in mind and nail that down in your mind as well, okay? And it seems a little brutal to nail this down. I don't mean to make anyone memorize, okay? But keep being aware of this. Put this in, when you're a first-time learner, put this as on some piece of paper side by side to you. Get yourself into that habit and keep referencing back as you work along with that. Okay, and then as you move on and as you have done repetitively enough, it will stay. Okay, so now let's look at part B. So let me introduce the following equation. So earlier it was a logarithmic equation in the sense that one single log term equal a value. Okay, let's look at the following. Log base 10 of x plus log base 10 of x plus 3 equals 1. Log base 10 of x plus log base 10 of x plus 3. Two log terms added together equals 1. All right, so I made it clear earlier that a logarithmic equation is in the form of a one single log term equal a constant value. Okay, so this equation here, I don't want anyone to rushly take this as a logarithmic equation yet. Okay, I'm saying not yet. The way I'm seeing it now is that it's not quite ordinary as the form we have seen back in part A right there, in a sense that there was one single log term and equal to a constant value. Here we got two log terms, okay, added together as I said earlier, and then equal 1. All right, but now let's go ahead and do our best right here to solve the work right here. And this is where I'm saying we apply our understanding of logarithms into solving equations like this. So for now, I'm not rushly going to say this is a logarithmic equation, because the world of logarithmic equations and equations that involve logs is a lot bigger than what we're hearing through the names right there. And so allow me to express my point of view that right now at this moment I only see this equation as an equation that involve logs. Okay, an equation that involves logs. It's not quite the standard logarithmic equation in the sense that there are multiple terms of the logarithms that we're seeing already in front of our eyes right here. Okay, but other than that, the standard technique that we've some experience we have done from part A can be carried over. The first step is to identify the domain, but then immediately, as I'm pointing out now, the first step is to find a domain. We are already having a great sense. We're already having a huge sense that we're facing a bigger challenge here. There are two separate log terms. Okay, so now let me point out the domains here. All right. So as far as the domain, that challenge we're facing currently is that we're having two separate log terms, and then assuming that anyone viewing this lesson has already learned from my lecture where we can define functions, logarithmic functions, then each one of these terms came from a logarithm function. And so this function here has its own domain. For this first term, the domain is, so just think a little bit of a scratch work. How about, let me write it on this space of the board right here. Just think of this simple log term right here. Okay. The domain for this log term is anywhere x greater than 0, anywhere that x is greater than 0, or in interval notation, anywhere between 0 and positive infinity in open interval. Okay. However, for the other function, for the other term which came from the function log base 10 of x plus 3, for the other term in our equation right there, the domain for this is different. The domain for this log term here is indeed x greater than minus 3. And again, I've had particular examples in my lecture where I introduced logarithm functions, where you've learned the solid technique, how I can come up with these domains right here so quickly. So here, allow me to just get straight into the point that the domain for this function, this logarithm function, the arguments of this logarithm is a little more than just a simple x variable. So the domain here is consequently x greater than negative 3. Okay, x greater than negative 3. Or in interval notation, we're writing that as the domain is anywhere between negative 3 and positive infinity. All right, so each one of these is the domain for the corresponding term right here. This interval from anywhere between 0 and infinity is the domain for this log term. This interval between negative 3 and infinity is for that log term. But the problem now is that our equation, look at the left-hand side of our equation. If we're looking at the left-hand side of our equation, it's a sum. It involves two log terms together. So we have to find an overall domain that meets both that meets the requirements of both log terms here. Okay, or in other words, another way of saying, we have to come up with a combined domain that satisfies both terms, being logarithm functions. All right, so in that way, here I'm seeing it for this domain right here as in the way how I see it, putting in a visual illustration would make it better. So this interval, okay, is anywhere from 0, is anywhere between 0 and infinity. Okay, and we are not including 0. Okay, but then this interval right here is on the line of number is anywhere between negative 3, and we're not including negative 3, and above 0. And so combining the two graphs here together, blending the two graphs here that represent the domain, and we're aiming at looking for a combined one domain that works for both terms right here. One domain that's possible for both terms. The only way, after we put that together, the only domain that we come out with is that domain anywhere from 0. So truly only that domain, that interval anywhere between 0 and infinity. That is the combined domain right here that works for both terms. Okay. So the combined domains happen to be the same as the domain for that term right here. But now this graph right here represents the combined domain. All right, so that's how I see it, and that's how I explain about that. So now with all the log terms here, the combined domain here has to be anywhere between 0 and positive infinity. Okay, and so now once we've had a domain, then whatever steps I'm about to show later on, once we've found a solution just similar to part A that we've done, once we've found some calculated value that we seems to be satisfying the equation here, we can only call that as a tentative solution. And then from there we're going to check to see any one of those tentative solutions, any one of those tentative values fall outside of this required domain. Okay, so that we can rule out of the list like that. Okay, and we only take those values that we solve for that still remain inside of this required domain. Okay, and once again, this is the domain that's the combined domain that satisfies the two logarithm terms right here. All right, so after spending some time explaining carefully about how to come up with the domain throughout all of your multiple log terms. So the idea now is that if you got here there are 2, even if you have 3 terms, 4 terms, 5 terms, 5 log terms altogether, for example, you got to come up with a domain that satisfies all 5 log terms. Each one of them has its own domain. The other one has its own domain. Each one of them has its own domain, and then we come up with a combined domain. That's the most original idea of how things work. Okay? Admittedly, if anyone feeling it's a little too much to come up with, to go through the logic right here, you are more than welcome to keep rewinding the process, the video, to see how I explained it. Okay, but now once we have arrived at the domain successfully, the combined domain, now we can start applying the logarithm properties, okay, to make things work right here. So with this equation, left hand side is the sum of 2 log terms, same base. That's the good news. Okay, the right hand side is a constant. So we can now apply our understanding regarding the properties of logarithm. Among the properties of logarithm, there's that one property I introduced in the properties of logarithms lecture, that we can turn from a sum of logarithms into a logarithm of a product. So in that way, I'm saying now the left hand side can be rewritten as, so now in my next step, the left hand side becomes 1 logarithm base 10. But then inside of that, what I have here now is a product of x times x plus 3. I just directly utilize that property we've used. Okay, that property we've used that property we've learned actually from that lecture where I introduced all the properties of logarithm. Okay, and so now that's how the left hand side became 1 single logarithm. We've done this skill back in that earlier lecture. And now all of that equals 1. All of that equals 1. Okay, and so now all of a sudden we realized one thing. Okay, and then we can rewrite. This step here is optional really. Somebody can decide to skip that. That's completely fine. At least if you are studying directly with me, I'm fine with this. Distributing out the x term right here to put the inside arguments of the logarithm in expanded form, that's going to be completely okay. And as a matter of fact, maybe we should, but skipping that is okay as well. So the inside argument of the logarithm here is an x squared plus 3x, but then in the end it's still a logarithm on top of an expression and equals 1. Okay, but now what I want to emphasize here is that all of a sudden we notice we have brought ourselves back to something where there's only 1 log term, equals a constant. Only 1 log term equals a constant. Okay, and so now, and I still didn't want to mention any other name or anything like that yet. But then at this point right here, now once we have brought ourselves to that form where it's only 1 log term and equals a constant. Now that understanding regarding log that I brought up earlier in part A, and that's only reasoning I've been using so far, can now be applied here again. This is that important understanding that I would like to emphasize. So we've learned through our lecture where I introduced about logarithm that specific skill where we learn how to rewrite an equation from logarithmic form to an equivalent equation, but in exponential form. One single term, one single log term equals a value, a constant, a whatever. Okay, and then we turn that equation from logarithmic form into an exponential form, an equation in exponential form. We're going to apply that exact understanding. Okay, we're going to apply this exact understanding. We've used this understanding and we apply that in part A, and now we're going to apply that again, simply because this equation now, all of a sudden we realize, well, disregarding all of that complicated looking expression inside of the log, in the end, one log term, log base 10 of whatever, etc. that is, equals a value. All right, so this is an equation in logarithmic form. So now I'm going to turn that into, all right, base 10. So I'm looking at 10 to power 1. Okay, so log base A of an expression x, big X, okay, big X, equals a value y. That's the same as base A to the y power to equal x squared plus 3x. Okay, x squared plus 3x equals 10. Or alternatively, we can rewrite this as the same as x squared plus 3x equals 10. But all of a sudden now at this point, I realize what we have made for ourselves, what we have produced for ourselves at this point here is a quadratic equation, where anyone at this learning point of yours, at this the point in your learning process, you have been well fluent with this. Okay, you have learned all of the essential skills how to solve a quadratic equation. All right, so now in that way right here, how you are going to solve for this equation, I can completely leave that for you. It's a quadratic equation. Maybe one more step is going to make it so clear that it's a quadratic. Okay, so I can just simply subtract 10 from both sides and lead to the resulting following equation. X squared plus 3x minus 10 equals 0. That's now clearly a quadratic equation. Okay, and so back to what I was saying earlier, anyone viewing the video lesson here, have your choice to use your own favorite method to solve for that particular quadratic equation. All right, so now it's just for me now, right at this moment when I'm looking at this, the factoring method comes more trivial for me for this problem, for this quadratic equation. But I'm not saying it's always. I'm not saying I'm always going to stick with the factoring method to solve the quadratic equation. So right now I see that I can factor this. So I still want to retain this, but back to my current step of solving the equation. I have x squared plus 3x minus 10 equals 0. Okay, I can factor this as x plus 5 times x minus 2 to equal 0. Okay, so now from this quadratic, we can easily come up with x equals negative 5 as one solution. But now instead of calling that the final solution, I'm calling that it's a tentative solution, a tentative x value that's satisfying the equation here at start. It's too lengthy to the point that I didn't want to mention it. Log base 10 of x plus etc. equals 1. So we found one tentative answer or solution in formal term. And then we found another one. So right from this factor right here, we have x equals 2. We have x equals 2. So we found two solutions. All right, but now see, there was a reason why I keep using that term, the tentative solution, and I'm probably the only one using that name right there, that terminology is a tentative solution. At this point, tentatively, we want to head out for these, but keep in mind there's a chance, there's a likeliness that some of these may get ruled out And that's why it's right now at this moment, before we finalize the solution, any one of these, which came right out from the math, and assuming we checked all our math steps carefully, nothing flaws or no flaws in any one of our steps right here, then we come up with these two answers. But only at this point right now, tentative answers right there. We have not finalized yet. Okay, so now what's left for us to do? We have to check, because there's a whole reason of coming up with domain. Okay, so now this is the second problem we're doing. So it's a good place now to really nail down this important understanding. It's anytime you're solving an equation that involves log. Okay, you may hear the name logarithmic equation, or log. In my term, I call that the equation involving logs, but even more general than logarithmic equations. Anytime you're solving an equation that involves logarithms, one term or multiple terms, or log and something else, we always have to check our tentative solution with the domain of all, with the combined domain of all the logarithms. Okay, we always have to check. All right, and this is the second problem here. First problem we checked, and that solution there worked. In part A, we checked that solution there worked. Now with this one here, we found two tentative solutions. Let's check them to find out if any of the candidates there fail to be the actual final solution. All right, so in that way, our combined domain of the two logarithm terms from the original equation here, our combined solution, our combined domain here is anywhere between 0 and positive infinity. So x must be positive. It means x is positive. So look at that. Look at the two tentative solutions here. That one immediately fails. X equals -5 fails the domain requirements. So now I have to take this out, because we only want x values that falls inside the domain. We only want any one of these tentative values to be inside of the domain if we want to go ahead and select that and finalize it as hey, this is our final solution. All right, so out of the two, and if we check for x equals 2 right here, x equals 2 is indeed inside of the domain. Okay, this domain from anywhere between 0 and positive infinity, that has x equals 2 in here. Okay, so now not anymore a tentative solution. This is now our final solution after we check. Okay, so now I'm saying that this equation, log base 10 of x plus log base 10 of x plus 3 equals 1, that original equation, okay, has only one solution, x equals 2. X equals 2. This is the only one, even though our solving work produced one extra value for us, but that was only a tentative one, and then we checked it, and that one failed right there. Okay, so use the domain is one of the important key, okay, of that narrow down your number of solutions like that you narrow it down, rule out some impossible solutions, and filter it out and only arrive at your final solution right there. Okay, so that's one important step. Get the domain of your log function, and get the domain of your log terms, okay, and come up with the combined domain of all log terms like that. Okay, but so if you look back, if you rewind the video and look back at my method, this is really the original idea. This is the real original idea, and it's just me when I teach any of the math course, I would like to deliver from the most original idea. So because hopefully there will be, it's not just hopefully, but there will be someone who desire to look at the most detailed aspect of mathematics. And so get the domain, and we have to always ensure our found solutions or any of the tentative solution meet with the domain requirements. That's the original idea. That's why originally finding the domain is one big step like that, one big key step that drives your solution and narrow down your solution set like that. Okay, But then, admittedly, throughout the work, and I was saying that earlier, if you rewind the work and try to go through my own explanation, it may be a little challenging at some point, because doing the work that coming up with a combined domain is not always easy. This problem is still okay, that you find one domain, you find another domain, we draw the graph and we combine it together. It's still okay, but it takes time. It's still okay, but it takes time. Okay, and so in that way, we're still looking at example 1 right here, and we're already done. Let me just swing back to that domain concept, checking with the domain concept of an equation involving logs right here, to show an alternative but quite common out there, outside from my teaching right here. This method I'm about to show is quite common. Okay, so getting down to the actual domain is just, I'm among some of the rare professors still showing this the original idea. But then the way to present this step right here in common practice out there is as following. Okay, so instead of going through so here's my little scratch page right here, and then let's come up with the domain again. So we can come up with the domain as following. As far as the domain, we can just keep it out as 2 separate lists, because we had 2 log terms. So one of them requires x greater than 0, and another one requires x greater than -3. But this is not really important. We don't even have to list this down. We just need to know this. Okay, and so now once we come up with 2 solutions tentatively. All right. So I'm rolling back to that point where before we finalize our solution. So now allow me to show you a different method to check which answer here can be ruled out. I'm gonna check. So instead of brutally finding a combined domain, we're just gonna check. Okay, when x equals -5, how do I check? I'm gonna substitute this into my equation. My equation on the left hand side is log base 10 of x, so it's log base 10 of -5 plus log base 10 of, so -5 plus 3 is a -2 equals 1. Can this satisfy the equality? After we substituted this tentative solution into our equation, our original equation. So again, this is an alternative method to check to check and find out who needs to be filtered out among your tentative solutions, aside from doing the formal domain work here, because I understand the domain work sometimes can become quite challenging. Okay, and it takes more experience. But so I show that original idea, but then now I'm pointing out right here, this is the much more common work that people out there aside, a lot of professors out there aside from me go with this method right here that directly deliver to the students right here. So you are also welcome to, anyone learning with me is also welcome to use this method. We just directly check. So we have to go through, we got 10 solutions, 10 tentative solutions, we check them all. So x equals -5. We substituted that value right into the equation. We ended up with log base 10 of -5 plus log base 10 of -2. We want that to equal 1, but I put double question mark here. Can this even be true? Can this even be true? Can this equality even be true? Well, and in the way how I see it can't even be true. It can't. Okay, why is that? Because now each one of these, see, I wrote down that scratch earlier. The domain for logarithm of x has to be positive. The domain for logarithm of x plus 3 any logarithm has to have an input value, an argument being positive. It's all negative here. So it's undefined for that one. It's undefined. For that one, it's also undefined. Okay? It's also undefined for the second term. And as long as only one term here fails, one term being undefined, then that means this solution fails. This tentative solution fails. Cannot be taken. And so I'm done. So now I'm down to, now I know that I'm ruling down that solution. I'm down to that other one. But don't rushly accept that just because we ruled that one and then we're gonna just take whatever left. Nope, we have one. If we go with the checking, we check all. And really, the two methods, even though I'm calling this as an alternative, it's used more commonly than the other methods right there. But in the end, they all have the same idea. We have to make sure our solution, our tentative solution, meets the domain requirements. That's the idea. Okay, so now when x equals 2, we have to also check that. We cannot just simply keep that, because I understand. The reason I mentioned this is because mentally there are students who are afraid of ruling out all tentative solutions. It's understandable, we've spent so much effort finding a whole bunch of them, and then we have to rule them all down to end up with a no solution. It is possible like that sometimes. Okay, so don't be afraid of checking all of your solutions, and we have to check all of your tentative solutions. So when x equals 2, how about let me write it up here, x equals 2. All right, substituting this into the equation, the original equation, log base 10 of x now becomes log base 10 of 2. Well, at least that first term works. It will give out a defined value plus log base 10 of x plus 3. But now when x is substituted by 2 right here, then it's going to be log base 10 of 5. And that equals 1. Okay, so now once we get to this, let's find out. Okay, let's find out if this equality really meets right here, then we're going to put a check mark right there. Okay, so log base 10 of 2 plus log base 10 of 5. Now we've learned our calculation. We've learned the log properties. We don't even need a calculator right here for this. I don't even need a calculator. See, it's the same as log base 10 of 2 times 5, which is 2 times 5 is 10. So log base 10 of 10 equals 1. Now I put a check there. All right, so now I know this solution will be the working one. This tentative solution is the one. All right. So I showed the original idea of coming up with the domain, the combined domain, okay, in this problem, part B. But then I pointed out that it had a weakness, even though it's the most original idea, but it had a weakness in a sense that it may be lengthy and a little challenging, a little over-challenging for someone who is not experienced enough with logarithm. For anyone who is actually not just someone, for anyone who is not experienced enough with logarithm, okay, then in that case right there, we can just bypass that step of finding the combined domain. But instead, if you bypass that solution, that work by finding the domain and check your tentative solution with the domain, then you can stay with this a little more common method right here. We check each solution. We check each one of our tentative solution. Check that with the original equation, and to ensure equality is reached. Okay, to ensure that equality is reached. So this is a check. So sometimes there's the downside of this. Sometimes if you can spend enough time to find one combined domain, then you got 10 solutions. You know immediately who's in that domain and who's out. I see a good advantage of that. Okay, but it takes experience of doing that. If we're going through this without coming up with the combined domain, if we're going with the checking method right here to check for a solution, then we have to, if we have 10 tentative solutions, we have to check for all. Okay, we have to check for all, and sometimes sadly the calculation might get a little lengthy. Okay, but that's the downside of that. But so it's all about any path that we are choosing, right, to get to the final destination. Any path we're choosing has a sort of like a side effect. All right, but I pointed out both solutions. But admittedly, in my teaching experience, more students favor this method right here, where you check each one of the solution, the tentative solution, because it makes it's closer, it requires less experience, and it's a little more direct for them, for the students. So for the rest of the problems in part A, I'm actually going to switch to use this mode right here, this style of checking your solution to make sure it works. Okay, all right. All right, so now in part C, let's continue to get comfortable with the standard steps to solve an equation that involves logs. Okay, I still didn't use any name yet. I call the next one I'm about to show here is an equation that involves logs. Okay, And then along the way, allow me to switch to the new style of checking your solution right here. Instead of coming up with a combined domain, because it takes experience. Okay, it takes some experience, but I highly encourage anyone learning with me to know both values. Okay, because who knows, any one of you learning from this lesson will someday in your future become a professor teaching math as well. Okay, so now in the next equation right here, log base 3 of an x squared, okay, equals 5 plus log base 3, all right, of an x plus 2. All right, so here again we got multiple log terms. The only good news left over for us is they're still having the same base here. They're all of the same base, but we got multiple log terms. Okay, and this is why I don't want to rushly call the equation, you know, a logarithmic equation or whatsoever. I just want to call it. I just want to point out at this point in how I see it, it's an equation that involves log. Okay, because now once you realize clearly that this is an equation that involves log, there will be in your lives at some point when you get more advanced in math, there will be some point in your future where you will run into an equation that involves logs on a couple terms, and the unknown at some other terms, but completely not the log terms. So non-log terms and log terms, unknowns all over. Okay, and so those equations there, good luck calling them the logarithmic equation. Okay, and so now and these, they still, every one of them looks different, but they still have some similarity that we can bring in one special method to solve for. Okay, so, and eventually I'm going to finalize all of that information. So now back to this equation, all I'm seeing here, log terms are all over the equation. Log terms are all over the equation. Okay, and then as I said earlier, I'm not going to worry about finding the domain here as my first step any longer, because that may become a little more challenging for a problem like this. So let's stick with that method where once we have found a possible list of tentative solutions, we're going to just directly check each solution into this original equation. That's all there is. All right, but now as far as, you know, getting the work done right here, allow me to swing on the other board. All right, so at this point right here, the reason I swing over to this board here to use this space to give out an advice. I want to pass down this advice for anyone learning with me right here. All right, so this is an advice, but I see it's been working with me throughout all those years. I've been handling, you know, equations that involves logs right here. See, we saw previously on the other board that log terms are all over the equation, left-hand side, right-hand side. This equation is still simple. The one that later on we're going to run into, there could be time where a couple log terms on one side and some other number of log terms on the other side. We may have 2 log terms on the left side, 4 log terms on the right-hand side. But in the main idea, log terms are spread all over your equation, left-hand side and right-hand side. Okay? So now this is the reason why I want to give out this advice right here. All right, so advice number 1. Bring all log terms. Bring all log terms to one side. Bring all log terms to one side. Okay. And then, so what about those non-log? And mainly these non-log terms that we're looking at here, they are constants. Okay. So what about those? We bring those. So bring all, how about I call non-log terms, okay? Bring all those non-log terms to the opposite side. All right. And so really, I mean, it's really just one advice, but I break it down into 2 steps like that. First step, bring all log terms to one side. And then all the non-log terms, we bring that to the opposite side. That's one big advice I have for for anyone who's about to to handle or to solve an equation that involves a logarithm. All right. So now with this advice, let's get back to the other board and see how this advice can be useful in our problem. All right, so now it's just me. Personally, I like to leave the log terms on the left-hand side, okay? And so now I'm going to subtract both. I'm going to subtract log base 3 of, I'm subtracting log base 3 of x plus 2 from both sides of my equation. Log base 3 of x plus 2. All right, so now consequently I'm ending up with the following equation. Log base 3 of x squared minus log base 3 of x plus 2, okay, and equals 5. So now let's check to see if my work here has satisfied that advice I've made earlier, or I just want to make sure my work here is aligned with the advice that was given previously. It was aligned with that. It's already aligned with that. All log terms are now brought to one side. The only non-log term is that constant 5 is on the opposite side. We're good with that advice. Okay, so now once we've checked that we have followed that guidance addressed in the advisory here, then so now we can see now, so at this point things starting to appear to be similar to that example part B we've done earlier, that problem we've done in part B. See, two log terms, same base 3, base 3. That's a good news. Okay, two log terms, but this time they're connected as a subtraction. It's a difference between the two log terms here. They're related as a difference of two log terms. All right, so now after we have learned about the properties of logarithm, we can apply some of those here. Okay, so the difference of two log terms, same base, that difference here can be rewritten in one single log term. So now one single log term, log base 3. Okay, so this is my next step right here. This is my next step after that. So this is just elementary stuff. I could have just skipped that. That leads to this, and this step right here leads to that next step. So the next step here, I'm combining these into a quotient. So there's x squared, I put it in the numerator. There's the x plus 2, I put that in the denominator. All right, so x squared over x plus 2 equals 5. All right, equals 5. All right, and I still don't want to use any official name or anything like that. I still see that this is an equation. No matter how we change the equation, we keep making it different and look different and look different. But in the end, I still don't want to get into any official name yet. But observation is telling me that now I'm down to one log term equal, one single log term equal a constant value. One single log term equals a constant value. And this is where again I can, so this is the third time I'm seeing this. I can again use this understanding that I have addressed earlier. Anytime we have an equation in logarithmic form, okay, an equation in logarithmic form where it's one single log term equals a constant, a value, then we can rewrite that equation in the equivalent, the logically equivalent form, but we call that exponential form. Same equation really, okay, but now it's a base a to the y, okay, to equals x, the expression inside there. All right, and so now to apply this understanding back on my board, I can now rewrite that as the following. So I can still use this little narrow space of my board like that. So now just like that, base is 3, so base 3 to the 5th power. Base 3 to the 5th power. And all that there equals the expression inside of my log. So this is the exponential form of my same equation. Okay, so now base 3 to the 5th power is x squared equal to x squared over x plus 2. Okay, base 3 to the 5th power, okay, equals x squared over x plus 2. All right, so now 3 to the 5th power in numerical, as a numerical value is 243. Okay, 3 to the 5th power, 3 times 3 times 3 times 3 times 3. All right, so now I can rearrange the equation as x squared equals 243 multiplied with x plus 2. Okay, and so I can even rewrite it further in a sense of, in a way that I'm distributing that 243 on the right hand side. So I'm ending up with x squared equals 243x plus 486. We have brought ourselves into another quadratic equation. Okay, we have brought ourselves into another quadratic equation. All right, and so when it comes to this point, okay, again, being a quadratic equation, you can go with any methods you want right here. Okay, anyone learning with me, anyone viewing this lesson, you can use whatever methods that you would like to use for that. It's just simply a quadratic. To make it even more clear, that quadratic I saw from the other board can be rewritten as x squared minus 243 x minus 486 equals 0. All right. And so now with something like this, I'm not patient enough to find the factoring form. See, even being the one who teaches here, I'm still not saying that I'm completely at that master level of all factoring problems. Okay, so that's why, you know, there's a good importance to realize that you can always flexibly use interchangeably between the 3 different methods how you solve a quadratic right there. So whatever we've learned in your previous course about the different methods to solve a quadratic, use that interchangeably and flexibly. Sometimes in some problem it's better to use a quadratic formula. Some other problem it's better to use the factoring, and some other problem it's faster to use complete the square or whatever. Okay, so here I'm going to say it's not really a faster one, but it's more solid. I'm going to stick with the quadratic formula. Okay, a equals 1, b equals minus 243, and that is a c right here, negative 486. Okay, so it's 243 plus and minus square root. Okay, and then minus 243 all square minus 4 times a, which is 1, and then times c here being minus 486. All right. And then I'm dividing that all by 2. All right. So now, and when it gets to this, we need a calculator here to help out with our work right here, to assist our work. So now quickly on the calculator, I'm going to go open parentheses, 243 plus, so I'm going to go ahead and head out with that plus 1 first. Okay, and then with this calculator here, it's strong enough to do all of the entire quadratic formula in one command, in one syntax right here. So 243 plus, and now I'm looking at the square root. And now open another parentheses, minus 243. Okay. All right, and it's still inside my square root, but I'm going to use arrow key to exit out of superscript mode. Minus 4 times a, which is 1, so no need to write it down, 4 times c, which is minus 486. Okay, let's close up parentheses. Now I'm going to get out of square root mode right there. All right, and so now I'm going to close that parentheses. So this is the numerator, and I'm dividing that by 2 in the denominator. Right, so that's our solution. That's our solution for one of them. And then the other one. Okay. Well, if your calculator is more basic than this one right here, then you can just spend some time retype the whole command here and change that to a subtraction. But here with this calculator, with this version right here, then I can also just See, scroll up and down to highlight a selected highlight a selected command right here, and just hit enter. That's gonna get the copy and paste. The exact same command is copy and paste, ready to be reused. But then I'm gonna scroll over, okay, and come back right back to that particular spot where it was a plus. Now I'm gonna change it to a subtract. Okay, and so now hit enter again, and we got a negative answer here. So these for now are the tentative answers. These are the two tentative answers. All right, so let's record them down. So the two tentative solutions I've found, one of them is a positive 244, okay, 0.98. And be aware, so here I'm using a calculator, so it makes sense that it's only going to give me, the high chance it's going to give me a numerical value in decimals, okay? But then do watch out that sometimes some professors require students to leave this answer in exact expression, okay? So it's only going to take your skills to simplify square root and all that, okay? So here I just want to focus on, we arrive at the tentative solution. So one of them is 244.98 and a lot longer, okay? And then the other one is a negative. The other one is a negative 1.983. All right, and so now we need to check. We definitely need to check. And so it's pretty nasty looking, and this is also another downside, but it's still gonna work. It's still gonna work. Another downside of this checking method right here, because the values are not so nice whole values. So when we're substituting this into the original equation, now I don't want to spend time coming back to the other equation, the other side, so allow me to just quickly write it here, right here. Log base 3 of x squared, okay, equals 5 plus log base 3 of x plus 2. This is the original equation. Okay, so that equation that log term has a square inside of that log term. And so now if we're substituting x equals 244.98 and a lot longer, if we substitute this whole value, this entire value, including all the decimals right here, into that left-hand side, at least it will work. Okay, at least it will come out being a value right here. Nothing with the undefined right there, because it's already positive and being squared it's positive, so nothing violating with the log. And then if we're substituting this into that right-hand side, we have the positive value plus another positive value, so it's still log base 3 of a positive value. So that means we're looking at the logarithm base 3 of 244.98 and a lot longer square. Okay, and then we want that to equal, we want to check if it's equal to 5 plus. We want to check if it's equal to 5 plus, and now log base 3 of negative 1.9, and actually 244, okay, 0.98 plus 2, okay, and then we're gonna have to spend time using the calculator and calculate this out. It will equal, okay, so I put a check mark right here. All right, it will equal. So now doing this, I see that we have the two sides here equal. Now we can go ahead and move on to the next one. So this one here reaches equality, okay. And then for the other tentative solutions, x equals negative 1.983 and a lot longer. Okay, I'm going to substitute that into each log term here. So on the left hand, so right now it's a negative sign. It's a negative value that we calculated. It rings a worrying bell right there. Okay, but let's just go ahead and put that into the equation and see what happens. So now, even though being negative here, but after substituting in, it's a square. So we square the x, we square the input. So now once input is negative 1.983, then the square is going to make it positive. All right, so I have left-hand side is log base 3 of negative 1.983, but squared again. So it's all going to be positive out. Right-hand side, we want to find out if it equals 2, and so that's my double question mark that we want to verify. if it equals to the right hand side being 5 plus, and now log base 3 of, and now it's a negative 1.983, okay, and a lot longer, plus with 2. Well, as far as meeting with the domain, this value is still fine. Okay, as far as meeting with the domain, this value is still fine, but then we still have to check to make sure it's equal. So, because the reason I'm saying it's still fine, because in the end, negative 1.983 is still less than 2. So adding 2, so negative 1.963 plus 2 is still going to give us a positive argument inside the log here. All right, so that's why now we can go ahead and use your own calculator. You can use whatever basic calculator you have, okay, and double check, and it will pass again. Okay, I put a check mark here, even though I did not swing over to my calculator station like that. All right, so now this equation we have found 2 solutions. We found 2 solutions for this equation. All right, so that's how another problem is done, and so I entirely head out for this checking method right here to ensure that all of our tentative solutions work, or none of them need to be ruled out, or to ensure that we have ruled out the correct one that fails the checking requirements, okay, the domain requirements for that. Because as soon as we fail the domain requirements, it's not going to work. It's not going to equal out. All right. All right, so let's look at another one right here, and I'm going to call that now part D of the example. So how about we're looking at log base 10 of x plus 12, and that there equals log base 10 of x plus log base 10 of 12, log base 10 of 12 like that. Okay, and so now this is where I was saying, just like to be consistent with what I was saying earlier, this is an equation where it involves logs, okay, and log terms are all over. Left side, right hand side, they're all log terms all over. We don't even see any constant terms. All right, so once again, and well, at this point we're far into that methods where we can skip that checking domain, we can skip that finding domain step, because we want to wait until at the last, at the ending step to check with all of our solutions, all of our tentative solutions. So we don't have to worry about checking the domain here, the combined domain for this particular equation. But now I see 2 log terms that has variables. 2 log terms on the 2 sides here having variables. And then there's still another log term, okay, being a constant term. So there's a constant term, but it appears to be in a log form still. All right, a lot going on, and that's why I don't want to rushly come up with any official name yet. Okay, and I don't want to rushly, I want to wait until when students have seen enough problems and see throughout all of these problems we've been through, and at least they all can be brought down to some similarity, and then eventually I'm going to come up with a formal name. Okay, so for this, instead of formally or officially calling that with a name, let's get directly to what I've been doing earlier. That advice I finally mentioned or introduced in part C right there as we went along. That advice. Let's now use that advice again. So now we have log terms all over the equation right there. 3 log terms all together. 1 on the left hand side, 2 terms on the right hand side. Okay, 1 on the left hand side, 2 on the right hand side. Let's bring all log terms to one side. Wait a minute. There's a log term here being a constant. It's okay, that advice of mine is still going to work. I just want to introduce one generalized but working anywhere method right here. So use that advice again, even though here it's just a constant, but it's worth your try. Okay, bring all log terms to one side. Okay, and then whatever non-log is on the opposite side. Okay, so here's how I'm proceeding. I'm going to subtract the log base 10 of x to the left hand side, and I'm going to subtract the log base 10 of 12 to the left hand side, and allow me to skip that elementary step right there by writing the subtraction underneath right there. I feel that it's a little too much now at this point. So after rearranging by subtracting those 2 terms to the left hand side, I produce my next equation as following. log base 10 of x plus 12 minus log base 10 of x minus log base 10 of 12 equals 0. That is the non-log term that I was talking about in my advice right there. So sometimes we don't have to, we don't even have to move some non-log terms to the opposite side, not really. As long as we have reached bringing all log terms to one side, okay, whatever remains there is already a non-log term. Fair enough. All right, so now in that way, there's a purpose of doing this. So now that property we've learned about logarithms applies again. And we've had that specific example in my earlier lecture where I was introducing the properties of logarithms. That in a lengthy expression like this where multiple log terms are involved, we have already had an example in that lecture where we've learned how to bring all of these, rewrite all of these, rewrite this entire lengthy expression on the left here into one single log term. Let's apply that again. So with the first two terms from the left to the right, I see a difference of two log terms. So now I can bring that into a log base 10 of x plus 12 over x. So two terms gets combined into one, but still we got minus a log base 10 of 12, a constant term, equals 0. All right, and then at this point, and then at this point, right here. All right, and so now and at this point, we can combine further. We can combine further. So now it's still a difference between the two remaining terms. One term came out as a combine of the two preceding terms. And so now I'm going to rewrite the whole thing here as a log base 10 of x plus 12 over x and divided by 12. That 12 came from here. And now that all equals 0. All of that there equals 0. Okay, and so that means in my next step, I'm ending up with log base 10. So now it's just a matter of simplifying down that expression inside of my log base 10 on the left-hand side a little further. Okay, so log base 10 of, so now I have x plus 12 divided by 12x. And then all of that equals 0. All right, now ladies and gentlemen, watching this lesson right here, once again, what have we realized that we have made here? What have we realized about what we have achieved here? From having log terms all over the equation, left-hand side and right-hand side, we have successfully brought it down to that similar form again. One log term equals a constant. One log term equals a constant. Okay, and it simply utilizes all of that properties we've learned regarding logarithms. All right. So, again, on this board of mine, allow me to erase all of those other details right here, except for this important fact that I was introducing. All right, so all we need, once again, for our current equation, we're at this step right here, where I see that as an equation in logarithmic form. One single log term equal a constant value. Okay, and then from this equation in logarithmic form here, I can rewrite that into an equation of in exponential form. All right, so in that way, here's how we can do it. Here's how we can work with that. So from my most recent step right there, I've had log base 10 of x plus 12 over 12x equals 0. So right from here and apply with this property into our equation, I can rewrite that as, so this equation is the same as base 10 to the 0 power to equal x plus 12 over 12x. Base 10 to the 0 I mean that value that was in that value on the opposite side of the logarithmic form equation now becomes a power. That's why I have base 10 raised to the power 0, because 0 was from the opposite side. All right, and then all of that, all of a sudden the log operation is gone. Okay, now all we have is just that expression inside of the log is here. So x plus 12 over 12x equals 10 to the 0. But 10 to the 0, this is just 1. So another way of saying, or in the next step, I'm writing this equation as x plus 12. My equation comes to one further step right here. X plus 12 over 12x equals 1, because 10 to the 0 equals 1. Anyone learning this in this lesson know well enough that a non-zero value raised to the 0 power equals 1. All right, so now in that case, now the next step of this, I'm going to multiply the 12x to the opposite side. So here I'm looking at x plus 12 equals 12x. All right, and so now I'm going to lead, this equation leads to, okay, 12 equals 11x. It's a simple, all of a sudden we realized right here, it's just a simple linear equation that we've been so fluent with. Okay, and so now 11x equals 12. Our tentative solution at this moment, tentative solution is x equals 12 over 11. Divided after I divided both sides here by 11. All right, so we found only one tentative solution. But good, the list has only one candidate, but do have a room to accept the fact that it could be, failing the requirements. Okay, this only one tentative candidate can be failing the requirements, making the whole equation, making the whole entire equation no solution. That may happen sometimes. Okay, that may happen sometimes. All right, so now I'm going to check. All right. And so at this point you can see that I really want to show the original method, but then at some point I still have to align my teaching with many other professors where the leading students into this route. It's not necessarily faster, but it's a lot easier to keep track of. Okay, whereas finding the formal domain originally, that original idea takes more experience. Okay, so now when we check, well, good thing we only have one tentative solution, 12 over 11. Okay, so now with 12 over 11, then this is what I'm doing. This is what I'm going to do right here. My left-hand side is a log of 12 over 11 plus 12. Okay, and I want to make sure it equals, so that's why I'm putting question mark here. I want to find out if it's equal, on the right-hand side, log base 10 of 12 over 11. Okay, plus log base 10 of 12. Okay, plus log base 10 of 12 right there. And yes, this will equal. All right, so I put a check here. So now this solution is not only a tentative solution, now it's a final solution. X equals 12 over 11. All right, so 4 problems in a row. This understanding is so far driving flawlessly throughout all problems so far. Anytime we can reach to one particular, anytime we can reach to one single log term equals a constant value, or a value, an expression, a single expression, then we can rewrite that from logarithmic form into an exponential form of the same equation, and the problem will be solved. Okay, and we can rewrite our equation and continue into coming down with the tentative solutions, and then check. All right, let's try one more problem. All right, so now part E of our example. So now I'm looking at natural log of x plus natural log of x minus 6 equals natural log of 6x. So this part E is a reinforcement of what we've done in part D earlier. It's just another problem where log terms are all over. Okay, log terms are all over the equation left-hand side and right-hand side. My left-hand side here has 2 terms. My right-hand side has 1 term. Okay, so let's handle this equation. Let's try to find the x value that satisfies left side equal right-hand side. All right. So in that experience we've had throughout part A and up until the one we just finished, now I want to bring in that same experience here. That advice, bring all log terms to one side, okay? And then if we don't see anything non-log term, of course, whatever left over on the right hand, of the opposite side, that's the non-log term, okay? So now I see a natural log of x here, a natural log of x minus 6, and a natural log of 6x. Okay, now for some students who are experienced enough with logarithm may see this as breaking it down as a natural log of 6 plus natural log of x. Okay, you can also approach that and then you cancel, but I actually, you can also approach that, but eventually it's going to be dangerous in a sense that you're going to cancel out the natural log of x right here. That can potentially dangerous in a sense that you take away solution, tentative solution. So stay away from that. Okay, so like I said, it's good that you recognize this, but it creates another danger right here where you may think about canceling that. I don't, it's not a working one. So now let's just stay with right here 3 log terms. Okay, I'm gonna bring all log terms to one side. So here I'm looking at, in my next step right here, natural log of x plus natural log of x minus 6 minus natural log of 6x equals 0. All right. So now just like that same experience we've had earlier, I'm going to combine log terms here into one single logarithm. See, 2 terms here are added together as a sum. So now I'm going to first end up with logarithm of x times x minus 6. Okay, or natural log of x times x minus 6. All right, and then minus another logarithm, natural log of 6x. All that there equals 0. All right, and then in my next step right here, okay, then we're ending up with the logarithm of, now I can combine these two into an x times x minus 6, okay, divided by 6x right there. All of that there equals 0. All right, and so now, so at this point, anyone watching this video, some of you may wonder how come, some of you may start thinking about canceling out this x right here. I still would say just leave them here. I mean, as some rare instances, we decide to go with the unsimplified expression right there. So let's leave them the same right now. Just like over here, I did not break that down into a natural log of 6 plus a natural log of x to cancel out the x, because there's still more waiting for us. So I just don't want to rule away solution, because these can likely give some solution, some x values. Okay, so now in that way, let's keep them the same, but all I see now is that one expression inside of the log equal a constant value. That's the turning point for us, a good turning point for us. I brought ourselves down to one expression, one log term equals a constant value, 0. All right, so now after seeing that understanding so many times, allow me not to swing to the other board to keep reminding you. Now I can rewrite this as, and this is now I realize it's an equation in logarithmic form. Log base e, okay, of this expression to equal 0. The only strange thing I'm doing, I did not cancel out the x here, even though more naturally anyone doing this would cancel that away. Okay, but in this rare circumstance right here, okay, then we're gonna keep that. So it only happens a lot of time. Mostly it happens just in the world of solving equation that involves logs. Okay. All right. So now in my next step, I can successfully turn that into x times x plus, x minus 6 divided by x, but equal, okay, e to the 0 power. Just like that equation. Okay, this is exponential form, base e of the number to the power that's from the opposite side of our log equation is here. Okay, and then equals to this. And it's supposedly 6x like that. E to the 0. E is a value non-zero, so raised to the 0 it equals 1. So now my equation really is, now to save myself some board space right here, allow me to just write that. So tentatively this is the next step like that. So 6 times x minus 6 over 6x. I'm still not going to cancel this. This is what I'm doing. I'm going to multiply both sides by 6x right here. That will leave me in my next step, x times 6 minus x equals 6x. Okay, and so in my next step, I'm going to distribute out my x right there. And that gives me x squared minus 6x to equal 6x. All right, x squared minus 6x to equal 6x. So now in this is what I've realized. This is a quadratic equation again. All right. So now I'm going to use this board space for my next work. All right, so from the very recent step like that, allow me to write it here again. X squared minus 6x equals 6x. Realizing that this is a quadratic, I'm going to bring that term to the opposite side, to the other side. So x squared minus 12x equals 0. All right, and so clearly factoring method here works a lot faster. I factor out a common factor x, making it x times x minus 12 equals 0. So I'm leading down to two tentative solutions. Two tentative solutions. That's why I said earlier, don't rushly cancel the x away. We may lose some solutions, some tentative, some possible candidates to be the final solution. So x equals 0 is one of them. See, and then x equals 12 right here. So let's roll back to what I said earlier a little bit. If we rushly cancel the x from here, then our equation would simply just become x minus 6 over 6. X minus 6 over 6 equals 1, where there were no x factor here. And then the equation would simply become just simply x minus 6 equals 6. X minus 6 equals 6 right there. Okay, and so x minus 6 equals 6 will just give you the one solution. So that would come out, that would filter out and only have this x equals 12 being one tentative solution. But see, that's threw away one tentative solution already, one possible candidate to be the final answer. That's why at some point, okay, we have to bypass the simplification and leave all of the values the same like that. All right, so now we have two tentative solutions. We can check. So now let's check. All right, for x equals 0, let's find out what's going to happen. If we substitute this into our original equation, natural log of 0 plus natural log of 0 minus 6. On the left-hand side, we want to find out if it's equal to natural log of 6 times 0 on the right-hand side. So now we don't even need to proceed into the evaluation. It's not going to work. So x equals 0 is a tentative solution, but it's not the real solution to this original equation because that's undefined. This is also undefined due to having taking logarithm of a negative eventually. This is due to taking logarithm of an undefined, so the whole equation just breaks down due to that value right there. All right, so now we don't want that solution. So now I'm going to rule that out. So now this is where we officially ruling it out. Okay, this is where we officially ruling it out. And so now, what about that one? What about that one? All right, so now when x equals 12, our left-hand side becomes natural log of 12 plus natural log of 12 minus 6. And we want that. We want to find out if it equals to the right-hand side natural log of 6 times 12. Okay, and now again, I just want to show how important that you understand that you already learned the properties of logarithm right here. For a problem like this, well, naturally, if I leave that for any students who are learning, who is learning about log, you very naturally enough that you're gonna pull out your calculator, punch it in for the left-hand side, punch it in for the right-hand side, and see if two sides equal. Yes, that is completely acceptable. Okay, but let me show you how you can also, even if you don't have a calculator, you can still do this. I don't have a calculator with me up here right now, and I don't mean to show off or anything like that, but I just want to point out the usefulness of knowing some math. Okay, this is log of 12. Let's leave it there. I don't need to evaluate that. This is log of natural log of 12 minus 6 is a 6. The right-hand side, we're still checking, but the right-hand side is a product. It's a product. Natural log of 6 plus natural log of 12. We've learned that from our lecture about the properties of logs. So now, needless to say, the two sides have to equal. We don't need to actually obtain the values right here. So now I put a check here. All right. So somewhere here and there, I just bring in personal experience with working with logs, with how I apply that, so that you can keep building your own experience. You see how I did that, and you build your own experience on that. All right. So now this equation right here, this original equation had one solution, even though the solving work gave us two. One of them was x equals 0, the other one is x equals 12, but only x equals 12 worked. So now at this point, solving all of these equations were logarithms involved right here. And I still didn't mention any formal name for that. Okay, then any one of these equations right here, we definitely have to check the value. So in any time, as a generality, anytime solving an equation where you have a log term, a couple log terms involved somewhere here and there, even one log term involved, you gotta check your final solution. Whatever you come up with before checking, we call that as a tentative solution. And then after checking, we can officially call those whatever, after being filtered out, whatever left or whatever still remain in your set, right there, we call that those are the final solutions. Okay, so now it's time to really finalize all of these ideas right here. So now as far as getting example 2 done, we got example 2 done, and we've learned a good amount of problems right there. Okay, and we've seen a lot of, a good amount of situations. Okay, so now it's time for me to mention that formal name right here. Yes, any of those equations we have done was a logarithmic equation. Any one of those, okay? So those were all logarithmic equations. Those problems we done, those problems we did in example 2, okay? Those were all logarithmic equations. What? I mean, it seems like from the beginning the professor here is only indicating, trying to make it clear that only the one in part A was regarded, that he called that a logarithmic equation, and then he keep trying to, you know, break people away from calling that a logarithmic equation, and now all of a sudden he's saying it again, that it's those were all logarithmic equations. Okay, so now allow me to tell this truth right here. The reason now we can officially say any of those we have done was a logarithmic equation simply because even though log terms were involved all over. But eventually we were able to, at the very final step before we solve a solution, we were able to bring that into the following form. One log term of whatever expression, big X, equals a value. See, look at part A was right out from the box, right here in this form. Then part B, then part C, starting to have terms crazy all over, so many log terms involved. That's why I didn't want any of my students to rushly regard to those at logarithmic equations, because I want to reserve, in my style of seeing logarithmic equations, this name, in my understanding, this name in the way how I see it is reserved for this special class right here. Anytime that you can bring your equation, so only if you can bring your equation into this form, one log term equals a constant, or yes, precisely a constant. Then we can call that as a logarithmic equation, because to make it consistent with the fact I've been using as the main driving force throughout the whole problem, throughout the entire example 2. Anytime we have an equation in logarithmic form, then we can rewrite that as the same equation but in exponential form right here. Okay, so for me specifically, and I'm among the one of the rare people who just reserve that special name for the logarithmic equation just for that, the class like that. Okay, so anytime you can reach one log term and equals a constant, that's where you can officially call that the logarithmic equation. The reason I'm doing this is that there are times now when I'm teaching a lesson like this, I'm not just gonna teach so that my students know how to solve this thing. I'm teaching, but but I constantly keep in mind that the preparation that any one of you, after learning this lesson, may or may not, but for those who decide to move on to even more advanced courses and much further advanced courses in mathematics. Okay, so what equation? So I brought in the terms that I so-called just simply log involved equation that involve logs, and not necessarily logarithmic equations. What are those? Because all of those that we've done in the end now, they're all logarithmic equations. So are there really just equations that involve log but not necessarily logarithmic equations? Yes, there are. Things like this you will see quite often in your calculus courses. Log base 10 of x equals x. Or if not calculus courses, in some numerical the approximation courses, you will see something like this. You see, this is where we got log terms involved, and then some other terms but not necessarily log and not constants. Something like this, I wouldn't call that logarithmic equation because it behaves completely differently, and the way to approach this, we can no longer use that property I've been driving throughout the whole the example any longer. Okay, we need to develop a different technique, different method to handle something like this. Okay, we can also sometimes we have log or natural log. Okay, my calculus 2 students, sometimes when I'm teaching a calculus course, my calculus 2 students run into an equation, a natural log of x, okay, and square plus 1, and then equals to a square root of x. See, the point is a log term and being involved with some non-log term, but they're all variable terms. Something like this, okay, they're not quite in the standard logarithmic equation, so I wouldn't call these the logarithmic equations because we will definitely fail to bring them into that form where one log terms equal a constant. Okay, so that main driving force solution. See, any of those examples in example 2, any of those that we've done in example 2, eventually we were able to use this central fact right here as the driving force to get the problem solved. But those I just now brought in the other board right there, this is not a clear cut any longer, or maybe we can't even use the method anymore. Okay, and that's why the logarithmic equation to me, okay, is just is any of those equations where eventually at some step you can bring it down to one logarithm term equal a constant, and then you can apply this understanding. That's where you can call that logarithmic equation. And so yes, I bet that I issue this challenge to anyone. If you search over the web and you type in the name logarithmic equation, you will only see those like you have done throughout the entire example too. Okay, but like in my teaching here, I would like to point out for you that there's still more outside of those that we've learned. Okay, so keep your eyes open. And so that's why when you hop onto the internet and you hear people say you really just use the term logarithmic equation all over the web like that without worrying about truly what it was. Okay, because a much bigger majority already assume that logarithm equation that anyone deal with is just among these that we can bring it here. And that's why you don't see much of those being mentioned outside of the logarithm equations being mentioned over the web. Okay, but they're still out there and ready for any one of you who would like to advance in your mathematical learning. All right, so but that's just a little bit of a development story outside of this discussion right here. All right, but then before I completely finish with this example, let me point out another fact that we concluded from our other details. Once we combine all the properties of log together, we can come up with the following fact. So the following fact is also a proven fact that can be that consequently came out after we've learned all the properties of logs. And then once upon learning this fact I'm about to show here, we can also use that as an alternative method to solve those logarithmic equations. So now I specifically talk about logarithmic equations. Okay, those equations where you can at some point you can bring them into a log term, and one single log term equal a constant on the opposite side. But now let me point out this alternative method right here. So if we start out with an equation in log form, okay, where we have one log term base a of x and equals log base a. Now notice right from the beginning, same base, log base a of y. So we have two log expressions equal with each other. Anytime we have that, then it leads to the following important. Then it's proven that x will equal y. The two expressions, the two arguments inside of our log will also equal, as long as we knew from the beginning that the two log expressions here were equal. Okay, and so now, well, how did this come about? How did this come about right here? How did this come about? Once in a rare occasions, once in a rare time right here, allow me to show a formal proof right here. How did that happen? Well, and I brought this up to enforce the understanding of something we have learned earlier in our lecture about the properties of log. Okay, so if, starting out with if, log base a of a capital X equals a log base a of a capital Y. Keep in mind that these big X and Y can be some expression instead of just the traditional plain old variables. Okay, so good thing they have same bases. So now we've learned this from elementary algebra. Anytime we have two numbers being equal, like say a equals b, okay, then we can raise them, we can treat them as a power, and so now with the same base here, we can raise them both sides. So x on the left hand side, x to the a will also equal to x to the b power. This is a known factor about powers right here that we should have seen this in our previous course. But of course, things like this not too often emphasized, okay, and understandable, because it has rare applications, but here we can use that. So now log base a of an expression x equals log base a of an expression y. If that was so, then I can purposely choose. And back at this property that I briefly remind you, then the x right here is basically chosen, any x, as long as it meets the requirements of being a base right here. Okay, so So now I'm gonna choose that A right here. That A. So I'm gonna raise my left hand side. I'm gonna raise base A to the power of log base A of x. And that will algebraically equal to base A raised to the power of log base A of y. I follow closely with this understanding from our past courses. All right. And so now, if we're looking at this a little more closely, now I have to remind you, so in my lecture, if it was my lecture, when I was introducing the properties of log, I talked about the property number 7. Okay, property number 7 is useful in a place like this. Okay, so you can go ahead and review what, at least within my lectures right here, you can go ahead and roll back to that other video of mine and find out what property 7 is all about. But now, according to property 7 of log, right there, the 7th property of log, then this left-hand side simply becomes x. And the right-hand side simply becomes y. So if this was true, then that consequently is also true from algebra understanding. And then from each one of these, consequently, we lead to x equals y. That's how I came up with that. That's why this is a formal proof. Formal proof here, it points out the bridges that connects from, hey, how come starting out knowing this equality, it leads to also knowing this equality. How did that happen? That's how it happened. Okay, so I didn't mean to show off the proof, so now I can put that away. Just want to bring it out to light that this is a known fact. My intention here is, after knowing this fact right here, we can indeed use that as an effective solution, as an effective method to solve a logarithmic equation as well. And we can also extend this to solving some equations that not necessarily logarithmic equations. Okay, not necessarily logarithmic equations, but just some equation that involve logs as well. This method can also be quite effective sometimes. Okay, so allow me to use this understanding here as an alternative method. And now I'm going to lead anyone viewing the lesson here into example 3. Okay, so all right, so example 3 here, allow me to write it down first. We want to solve each of the equations, right? Or just each equation for x. We just want to solve each equation for x. This is example 3. We still want to solve logarithmic equations. Okay? And as I said, the method I'm about to introduce here may also work for some other equation that simply involve logs, but not necessarily logarithmic equations. But I want to particularly focus to apply this method on the logarithmic equations now. Okay, so now part A of the example, allow me to bring in the following one. All right, so how about log base 10 of x plus 12 equals log base 10 of x plus log base 10 of 12. All right. I paused here a little bit simply for you to understand one thing. If you've been watching this lecture here continuously from beginning to now, here, you realize, at least if you have gone through example 2 with me carefully, then you realize this problem I selected from example 2 right here. Okay, this was example 2 part. So this one right here is from example 2 part D that we did. Okay, so I just want to point out that the same equation, yes, so at this point we were clear that this equation was a logarithmic equation, and it is now a logarithmic equation. Okay, it's just a matter of knowing how to turn that into the form of a one single log equals a constant. Okay, that's why it's a logarithmic equation. And so, but now if we roll back from the beginning point where we just, hey, this is an equation that involves logs and we need to handle it. See, if we roll back, even ignoring, roll back to that point where we even ignore about the names like that, ignoring about whether or not we can successfully bring all this into one logarithm form, one logarithmic term equals a constant. If we roll back to that point like that, then we have the following alternative methods right here. So the advice that I introduced in example 2 is not necessarily useful here. I don't have to necessarily use that advice actually. I don't need to move all so that advice that bring all terms, all log terms to one side, we don't necessarily have to follow that guideline, that advice here. If we are going with this method I'm about to show over here, let's leave them the way that it is right now. So we got a couple log terms here and a couple log terms there, but you see one thing I see in this equation. Aside from these log terms, there's no other terms being non-log. There's no trivial non-log terms. I mean, there's no constant term around anywhere. Only log terms. So a couple log terms on one side, a couple log terms on the other side. That's all. Okay? A couple log terms on one side, a couple log terms on the other side. That's one thing I see. So now, I'm going to put away the advice about bringing all log terms to one side. I'm going to stay right here with this equation. Left-hand side has only one term, then let's leave it like that. Let's leave it the way it is on the left-hand side. Okay, but right-hand side, I can now apply. See, there are two log terms. It's a constant term, but it's a log term. So I'm going to combine the two terms here together in one logarithmic expression as one single logarithm, as you have seen in that earlier lecture where I introduced the properties of logarithm. And so now the sum of two log terms, same base. Now I can rewrite this as a log base 10 of 12x. It's completely legal for doing that. And now I have achieved that form of one single log term equals another single log term with the variable on the opposite side. One single log term of an expression equal a single log term of another expression. All right. So with this point right here, allow me to take a quick pause and swing over to the other board. One single log term of an expression equals one single log term. So now, in the way how I see it, at this moment, this equation is telling me that, hey, if we know we have this, then what can happen? If we know we have this equality, or if we know we want this equality to happen, if we want this equality to happen, then what can happen next? Okay, if that was true right here, then what would be next? Then now applying that property I wrote down on the other board. See, one single log equals another single log of different expressions. Okay, now it leads to x plus 12 equals 12x. It may be a little faster in using this method, but it doesn't always work. It only works where you know how to turn your equation into one log equals another log on the opposite side, one single log on each side only, if you know how to make your way there. Okay, so start combining your creativity right here. I've shown two different methods right there. Okay, the other methods we've learned in example 2 work more universally, but this method can make the process a lot faster if we recognize it. So now in this problem right here, here's how I'm seeing it. Well, now this is clearly a linear equation. So I'm going to subtract the x to the other side and leave the 12 here. So I'm looking at 12 equals 11x. And now x equals 12 over 11. And again, in the end, we're still solving a logarithmic equation. So we still need to, even though the different methods or whatever, the method does not guarantee that your tentative solution will work. So we have to check. Let's check. Okay, let's check. Okay, so now when we check, okay, the only solution we found, 12 over 11. Okay, we're going to substitute that into the equation again. Left-hand side gives me log base 10 of 12 over 11 plus a 12. I want to find out, as question mark right here, I want to find out if it will equal to log base 10 of a 12 over 11 plus log base 10 of a 12. Let's find out if that's true. Okay, I thought it would be useful, but I forgot to mention this. Admittedly, I forgot to mention it. Or it could have also been at some moments earlier that I thought I may have saved this for the later ones. Okay, but here it is. I could have mentioned this in the earlier example. We don't even need a calculator to verify that the left-hand side here equals the right-hand side here. We don't even need that. Okay, we don't even need that. I could have mentioned that, but like I said, it could have been I forgot, or it could have been that now I can't remember anymore the reason why I did not do that earlier. But I could have pointed out the following. Again, what if we didn't have a calculator? Log base 10 of a 12 over 11 plus 12. Okay, it's the same. Now this is truthfully, if we make common denominator inside of the log right here, it's log base 10 of a 12 plus 11 times 12 divided by 11. Admittedly, okay, and that equals log of, so now I'm going to factor out a common factor 12 right here. Okay, so 12 times, so 1 plus 11 over 11. So this is really a logarithm of a 12 times 1 plus 11 is another 12 right here, 12 over 11. So really, all this is now all of a sudden I realized that is the same as the product of a 12 times another 12 over 11. That's why it can now legally equal to log base 10 of 12 plus log base 10 of 12 over 11 on the other side right there. I didn't need a calculator. I didn't even have to punch a button right there. And I can still verify that equality was reached for that problem. And that problem was the checking work in example 2, part D that we've done earlier. And now I brought it out to light. Another personal experience to show how useful your understanding in the properties of log can be for you. All right, so now x equals 12 over 11 is no longer a tentative solution. It's now an official final solution right there. And look at how many steps we have done. So with this alternative method, for some equation, once it works, it will be a lot faster. Okay, so now that I've shown two methods right here, and sometimes this method works faster, then it seems so far that this method works faster, but I said it doesn't always work. It doesn't always work. And so in that case right here, with the two methods, how do you know which one to choose to go for? Well, then here's my advice. Naturally, we're going to head out for the easier methods first, the method that's safe, or the faster method first, the method that has less steps for us. Let's head out for that here. But then if we run into challenges, because the major challenge for shooting for this method is to turn your equation into the form where you have only one single log term equal that single log equal that another one single log term on the opposite side. Same base, but different expression. If we can make our way turning the equation into that primary form right there, then the method we've learned here work directly. But otherwise, again, naturally we head out for the faster method. And if that method at some point become no longer a fast method anymore, we switch to the one that's more trivial but takes longer steps. All right, let's try it again to see how useful that other method I just pointed out can be. All right, so now let's look at part B of the example. So now we have here what we have here, natural log of x plus natural log of x minus 6 equals natural log of 6x. All right, and yes, admittedly, this problem I selected that from example 2E that we've done earlier. Okay, but now I want to introduce a completely brand new method, a completely different method to solve this. And yes, we call this, we eventually agree that it was also a logarithmic equation. Okay, but now to look at this equation, let's roll back to solve this equation applying the new method we've learned here. Let's roll back to that point where we were not even sure if we can bring this into a 1 log equals a constant on the other side. We don't even need to worry about that. And let's put away the advice about bringing all log terms to one side. We don't need that advice here for this method. For this method, we aim at how we can turn the equation into only one log term on one side and equal to another log term of the same kind on the other side. A log term of the same kind, I mean same base, but not necessarily same expression inside. Okay, let's get to it. So now I see left hand side here, there are two terms, but they are terms, so we can add them. So the sum here can be turned into a logarithm of x times x minus 6. The logarithm, a natural log of a product right there. Log base e of x equals x minus 6. And that now equals a natural log of 6x. Now we have achieved what we wanted. We have achieved what we wanted. One single logarithm term equals another single logarithm term, same base, okay, but it could be a different expression right there. All right, and so now from this equation, this is clearly making way for us to use that property, that important fact that we've learned here. Anytime we've reached to one logarithm expression equal to another single logarithm expression of the same base, if that's so, if that is true, then now automatically the two expressions inside the logs here will equal on the two sides of our equation. All right. And so for that reason, in this way, how I'm seeing automatically from this point, automatically I'll lead to x times x minus 6 will equal 6x. Okay, and then you can still take that advice from me in when we were doing this problem in example 2, that don't cancel out the x here because we can potentially lose some solutions. Okay, so the proper way of doing that, okay, x, we can multiply x into each term there. So now we have x squared minus 6x, and that equals 6x. So now this equation here turns into x squared minus 12x equals 0. And we can quickly lead to a factoring form, x minus 12 times x to equal 0. And then we can quickly lead to x equals 0 and x equals 12. These are the two tentative solutions. And so it's a lot faster than the approach we try in part B, in example 2, part E right there. Okay, but it's just faster simply because here we can easily bring that into the one logarithm equal another logarithm of the same kind on the opposite side. But not all logarithmic equations can be brought into this form. So be able to use two different methods anytime that you need to. Okay, I just give you more options to handle a problem right there. Okay, and so now we're going to check. After we found two tentative solutions, we're going to check again. X equals 0, and again, I just want to go through every little detail to point out, even if we use a different method, an alternative method, it's still not going to be anything different with how we conclude the final answer. So we still need to check. So when x equals 0, our original equation appears as following: natural log of 0 plus natural log of 0 minus 6, and we wanted that to equal to, and that's why I'm putting question mark, natural log of 6 times 0. Okay, that's 0, undefined for log. This will give me a natural log of a negative 6. That's again undefined for log. This will give me a natural log of 0, another undefined for log. So clearly x equals 0 has to be ruled out right there. All right. So in that case, this tentative solution cannot be used right there. But do not rushly assume that this will be our remaining solution. Nope, we got to check carefully for each one of those. All right, so let's check for x equals 12. All right, so when x equals 12, we're looking at natural log of 12 plus natural log of 12 minus 6 equals natural log of 6 times 12 right here. And I have shown my checking work when we finish with this example 2 part E right there. So allow me to ignore that. We know that we're gonna put a check mark here. The two sides will equal. All right. And so that means our final solution for this equation, x equals 12, is now concluded. Okay, that's our final solution for that. All right. All right, so now just like how I was doing that after example 1 right here, I want to give an insight about why do we have to face these problems about solving logarithmic equations, or even more generally those equations that involving logs. I mean, why do we even have to run into these problems first in line? Okay, because now, like what I was saying in the beginning of the lecture here, this lecture here requires that you have learned about, we can define, well, after we've learned about what a logarithm operation is, we can define a logarithm function. Okay, so let's pick a quick problem, for example. So in some of our problems that we've done earlier, there was, how about log base 10 of x, okay? Log base 10 of x plus 12 equals to log base 10 of x plus log base 10 of 12. All right, so the reason that we arrive at an equation like this, so that it produces that challenge for us to solve equation and calling that a logarithmic equation, simply because the left-hand side can be regarded as a function f of x, where, see, we define f of x as log base 10 of x plus 12. So after our learning and after I raise out your awareness that now we can define a function as a rule using logarithm to define a function, then now it's, see, that left-hand side is a logarithmic function. Before I head on to that on the right-hand side, quickly on the board right here, this is log base 10. This is the graph for log base 10 of x plus 12. All right, and now I purposely hid away all of the numbers and the grids right here, so that you can see just mainly focus on the shape right here. So the graph here is primarily right now is a curve, some kind of curve, some kind of shape right there. Okay. And then, once I recognize the left-hand side as an equation, as a function of a logarithmic function, then the right-hand side can also be regarded as, so I can see that as another function. How about g of x is defined as log base 10 of x, okay? Plus with a constant term being the value log base 10 of 12. So right-hand side can also be regarded as a function. In that definition, log base 10 of x plus log base 10 of 12 like that. It's a constant value. Okay? And so now the graph here that you're seeing is the graph for the left-hand side. So now let me pull up the graph of the right-hand side right here. All right, so this is the graph for log base 10 of x plus log base 10 of 12. And so now I'm putting the two graphs together. All right, the graph in red color here is the graph for log base 10 of x plus 12, and the graph in the blue color here is the graph for log base 10 of x plus log base 10 of 12. Okay, and apparently right here in the picture there will be a point where the two graphs crossing each other. The graph in red and the graph in blue are crossing each other. And so in that way, solving an equation like this means, there were a lot of occasions. There are a lot of occasions. Not only there are a lot of occasions where we need to come up with an x value satisfying, or we need to find out the x value where the two graphs here are crossing each other. They're crossing each other. Okay? And so we found out earlier in our work. That the value for this was 12x equals 12 over 11. Okay, and we already checked and proven all that. Okay, and so 12 over 11 with machinery with decimals I'm using, that value in decimals value is about 1.091. Okay, but in the end, see, ultimately the very first reason why we solve any equation, is that we treat each side of an equation as a function. And so we want to find the x value, the variable value, where the input variable where it's making the two graphs crossing each other. And so if we find more than one solution, that means the graphs crossing each other at multiple points. All right, and that's one of the reasons why we ended up with these challenges about solving an equation, a logarithmic equation, and even in more advanced courses later on that you go through solving an equation where it's solving an equation that involve logs but not necessarily regarded as a logarithmic equation. Okay,